Today, Rob Swanson is our instructor, and today we're doing Chapter 15, Safety, Chapter 16, Climbing. We'll have a little 15-minute break, and then we will finish up with Risk Assessment, Chapter 12. Good morning, everybody.
So we'll get started with Chapter 15 here, the tree worker safety. I've encouraged you to, reach out and look for those ANSI standards on a few of the other presentations we've done so far. Most of those have been centered around the A300 specifications. Today, we're going to talk about a few others. Our industry over time has been associated with forestry and with the mining industry. So our hard hats and our hearing protection and our eye protection, some of those standards were originally written for mining. And then there's been some additional things that have come in over time that have been brought in by the forestry industry. We have an organization that is the TCIA, the Tree Care Industry Association, and at one time they were the National Arborist Association, the NAA. And back when they were the NAA, they were one of the largest lobbying bodies, or they are the largest lobbying body for our industry with the government. So they're the ones that are trying to try to get us separated from forestry, where we are our own entity, hoping to lower our workers' comp and things like that, but also to introduce things that are specific to safety and our industry. So to get on with it, our first set of standards, you're going to look for these ANSI Z133. This is the base standard. They were modified in 2017. So you're going to see the Z133-2017. I encourage you to also purchase I've talked about purchasing the A300s. I would also consider purchasing these as well. It's going to go over things like the personal protective equipment. We'll talk about work zone procedures, potential hazards near electrical conductors. We'll discuss MAD, the minimum approach distance to energized conductors and things that might become energized. Talk about chainsaw and chipper operating procedures. So our tree worker safety stuff, with the ANSI again, the Z133s, we're going to talk a lot about laws and regulations, things that you have to do and things that are suggested and why they are suggested instead of required. The Occupational Safety and Health Act in the United States is what established the Occupational Safety and Health Administration, otherwise known as OSHA. The purpose of OSHA is to reduce occupational injuries, to keep us from getting hurt on the job. OSHA has established many regulations that affect arboricultural work. So we have, again, the Z133s. These are the set of standards for arboricultural operations approved by the American National Standards Institute. So there's ANSI. So here's ANSI are the guidelines, and OSHA is the enforcing body. So not all ANSI standards are enforceable by law, but all OSHA standards are enforceable. It's intended, again, to provide safety standards for workers engaged in our industry. It's important that all tree care workers to be familiar with and comply with the ANSI Z133 standards, as well as all the other applicable OSHA regulations. Again, so that not all of our stuff is under Z133. The word approved appears on equipment. You'll have approved chainsaws, approved saw chaps, approved eye protection, things like that. So if it's an item, it will have the word approved on it. Shall denotes a mandatory requirement. You shall wear protective saw chaps while operating a chainsaw on the ground. things like that. You shall wear protection when involved in tree care operations. Should notes an advisory recommendation. So when they use the word should, it's not really a choice, but the topic just happens to be so broad that they can't drill down and say shall, because our industry has a lot of different people in it. So we have salespeople, we have business owners, we have climbers, we have ground operators, we have bucket truck operators. So and each one of those has its own set of shalls associated with it. But in general, we might use the word should. You should wear protective headgear when involved in tree care operations. Well, protective headwear is not necessarily going to be the same for the sales guy that shows up on the job. He still has to wear a hard hat that is approved, but that hard hat might not have to meet the same criteria that the climber has to meet. That's just an example, but that's why they use the word should here. So both of them are defined as used in tree care operations, but you have much different job functions. So you should wear protective headgear. So personal protective equipment, these are called PPEs. Employers shall require employees to wear clothing and footwear appropriate for work conditions. Again, we have that word shall pop up here. So you shall wear the appropriate equipment, but that appropriate equipment might be different, again, for the type of person on the job. All employees shall wear eye protection approved by the ANSI Z87.1. This was updated in 2010. In addition to eye protection, hearing protection should be worn if sound levels are expected to be above 8 hours at 85 dB on a time-weighted average, TWA, time-weighted average. And the ANSI standard for the helmet is the Z89.1. So I think the Z87 is a forestry and Z89 is mining. But what this means to this hearing protection business, some of the larger companies out there have to undergo audio audits on an annual basis. One of my first employers, we had to wear these little meters on our belt loops for an entire day. And what that meter did was it accumulated the sound levels in decibels that we were exposed to over the course of our workday. And so if that turned out to where we were presented with over 85 decibels of sound on average for 8 hours, that means you have to wear hearing protection. So if you're the sales guy and you show up and they're running the chipper and you're over there for a few minutes and you get back in your truck and leave, you might not necessarily have to wear hearing protection because you're not going to meet that 85 dB on over an 8-hour period. You're just exposed to a high amount of noise for a short period of time. Sound damage is cumulative. So that's where this comes from. That way we can sort of define who has to wear. So if you're on a crew, you're operating chainsaws throughout the day, you're operating chippers throughout the day, these things are definitely going to get you into this range where hearing protection is a requirement. Here's some examples of personal protective equipment. We have a chainsaw here with its chain brake in place. All the safety features seem to be at least present on this chainsaw. We have our sturdy boots. We have a helmet that's approved. We have hearing protection attached to it, the muff style. We have a face screen. This by itself does not really count as 100% eye protection. You still have to wear the eye protection. So here we have our jewelry. So jewelry really should not be worn, especially if it dangles about. You want to make sure and remove that at the beginning of every day. So it says jewelry should not be worn because it may catch in equipment. So it's not a shell, but if you do have anything that dangles, no hoop earrings, no chains, nothing that can get caught in brush as it's being pulled into a chipper, that sort of thing. All tree workers shall wear head protection that's in compliance with Z89.1. eye protection shall be worn when performing tree work. So if you're anything other than being on break, you should wear eye protection and a hard hat. So hearing protection is required for workers who are exposed to loud equipment for the prolonged period of time. So again, that's 85 dB on a time-weighted average, TWA. Gloves are strongly recommended for certain operations, such as sharpening chainsaws and chipping brush. Gauntlet-style gloves should not be worn when operating chippers. If you're an employer, make sure that you're not providing gauntlet-type gloves. What's a gauntlet-type glove? So these are the ones that sort of have a cuff, that big stiff cuff. Now, you don't want to wear those. You want to wear things that are closed, because you don't want brush being stuck on the inside of the glove and then being pulled into a chipper. Here's some additional protective gear. All tree workers should wear sturdy boots. Notice sturdy boots is really not defined either. It's a pretty vague term, sturdy boots. If you're going to wear spikes for most of the day, you're going to want a good heel on your footwear so that spike's held in place right. But good sturdy boots should always be worn. No tennis shoes. Leg protection must be worn when using a chainsaw on the ground. Chaps or chainsaw pants. So these chainsaw pants, these are chaps. They have a type of material inside of them. It's a Kevlar fiber. When a running chain touches this stuff, it tears open, and these long fibers immediately get pulled into the chainsaw, into the clutch, and it just seizes the clutch up and the chain stops turning. They do make pants with these things built into the pants. So the chainsaw pants, like if you go to Arborwear or something like that, and you look up these chainsaw pants, you're going to quickly find out they're about $600 a pair. It's not cheap stuff, but it is designed, again, to stop that chain so that you're not doing a lot of damage to yourself. So one of my close friends here in my area, his name is Andrew Machuca. Andrew he's a world-class climber. He goes around the world competing in the climbing championships. So here's a picture of Andrew up here using all of his safety gear. He's got his gloves on. He's tied in. He has ground people working for him. He's doing, he's butt hitching this piece out of here. Or actually, I think he might be dropping that piece. It's hard to tell from this angle. But he's got on his sturdy boots. He has on his $600-something pair of chainsaw chaps and all of his associated safety gear here. So this is sort of typical. I'm going to try to work in some pictures in the climbing section that I took the other day of another friend of mine, Jimmy Pritchard. Jimmy was the guy who competed for the U.S. this past year in the internationals. On a job site, good communication skills are absolutely essential. It's an integral part to worker safety to have everyone on the same page when you're on a work site. Each worker on the crew must be aware of what the others are doing, and each must take measures to prevent accidents. You're not, always rely on yourself to not get into an accident, to identify risks and hazards on a job site, but share those at the beginning of the day. We'll talk about that in just a second. There must be a clear and efficient means of communication between climbers and ground workers. You want to make sure that the landing or drop zones are well defined and that you have a command and response system in place. The landing zone is a predetermined area where cut branches will be brought down in a rigging operation. Whenever you see the word rigging, that means that it's going to be on a rope. You're not just going to cut it, break it loose, and drop it. You're going to land it, so you're going to control it all the way to the ground. So that's a landing operation, which will be done with rope. The other area that we define is the drop zone. This is an area where cut branches will be dropped off, or you're attempting to get them into that space each time, but they are not on a rope. So back to this sort of voice command and response system. You might say something, if you're the climber and you've cut a piece and you're about to drop it down into your drop zone, you might say stand clear, but you're not just going to say stand clear and let it go. You're going to say stand clear, and then you're going to wait for the response, all clear, and then you drop it. These words used here, stand clear and all clear, it doesn't matter what words you use as long as it is consistent on the job site and typically consistent in the company, especially if you have employees that move from truck to truck or from foreman to foreman on a daily basis. Make sure your whole company is using the same command and response signals. Hand signals can also be used as well. This is kind of handy because you're getting a good visual. You're looking around, you have two guys on the ground, you're looking for both guys, they're both giving you the thumbs up. You know where they are, so that's a good way to stay in touch as well. In modern arboriculture, on many of the sites you go to today, they have Bluetooth helmets where you're wearing noise canceling, so you're meeting your hearing protection standard by wearing those. In those, they have a communication system with everybody on the crew, so it's kind of like this giant group chat, but you can speak and it's picked up by everyone on your crew. So it's kind of a two-way radio system so that you can say, okay, I'm about to drop this. Is everybody clear? And then you listen for all their feedback, and then you can let it go. Each job should begin with a job briefing. This coordinates the activities of every worker. This is where you're going to pull everyone's eyes together. This is a brief meeting of the crew at the start of every job to communicate the work plan and responsibilities and requirements and any potential hazards. I like to take my crews and walk them over the entire site. Even if you're a ground worker and it's your first day on the job, you might be the one that finds a stump hole hidden in the English ivy that you can't see. So you find that, you might put a cone on it, you're going to identify, hey, this is a trip hazard. Somebody else might find guy lines or a power line that the sales guy might not have seen or noted on the work order or something like that. So going over these at the beginning with everybody, everyone's going to be aware of it. So one person finds it, everyone else is going to know about it in the line. Another thing to do is this work plan. This is a predetermined orderly means for getting the job done. When we go out to do a job, it's not always just one tree in the front yard. We might have a tree in the front yard and a tree in the backyard. We might have a 5-man crew with 2 climbers, 3 grounds guys, or 2 grounds guys and someone to run ropes in the rigging operations. So give everyone their assignments. If we have so many chips during the day, who's going to take the chip truck to the dump to go take care of the chips? Who's going to be in charge of where we're going to leave the chipper when the chip truck takes off? Who's going to be in charge of the bucket truck for the day? Who's going to be in charge of the grapple truck? Or who's dragging brush? Where are we going to stage the brush? Who's going to be the climbers? Who's going to attend each climber? Things like that. Define all that at the beginning of the day so that everybody knows and everybody's on the same page. One of the things that I like to say during this sort of portion of it is that when I first started in the industry, we had pieces of paper for our work order, and that piece of paper was laid on the dash of the truck. And on that piece of paper, we might have things like the address of where we're going. So if you did have an emergency and you have to call 911, you have that address right there where you can pull it out. The person who's calling 911 is going to have the physical address of the job site. Now we've moved to these digital formats, maybe on your personal cell phone that might be up in the tree with the lead climber, or it might be on a tablet that is locked for security reasons and it's laid on the dash of the truck. Everyone needs to know how to access the physical location of your job site. So even if you just have a groundman on the job, make sure that groundman has access and knows how to get access to that information. General safety at the work site begins with proper training. Everyone must be adequately trained for the piece of equipment that they're on, and that should be documented. You can't just have your groundman on the first day walk up and operate a chipper. You have to have that person documented as being trained on that piece of equipment. when you're even dragging brush for the first day that you hire somebody, maybe you should sit them down in the office and explain what brush dragging is. You're going to make sure that you're not pulling ropes that's getting caught up in the brush. The ends are all facing in the same direction. You're going to stage it up over here so that we have easy access to the chippers, and then go over what the hazards might be, the trip hazards, keeping your shoelaces tied, not wearing dangly jewelry or open shirts, gauntlet style gloves, all that you need to document that you've done all that so that they understand their job position. And that needs to happen at every level on your job site, so that the people on the chippers are trained to operate chippers, and the people who operate chainsaws are trained and documented to operate those chainsaws. So be sure that you've established these safe work procedures. It is recommended that all workers receive training in CPR and first aid. Most companies have either an annual opportunity to do this, or they will send you off one at a time to your local Red Cross to get certified in CPR. Larger companies might have a CPR instructor come to your company and do it one-on-one. First aid and CPR, there's very few small accidents in tree care. If you do have an accident in tree care, it can be quite major. So make sure that you have the appropriate and adequately stocked first aid kits. These shall be provided on each truck. Now, the reason that they don't really define this is because we don't know what kind of truck it's going to be. Your sales guy, his biggest problem, there's no telling what his biggest problem might be. It might be, he might get splinters or minor injuries. So does he need a first responders bag in his truck to take care of his personal problems? No. On a tree care truck, are they going to need something like a first responders? Probably so. Again, there are no real small accidents out there. You want to be able to handle major lacerations or exposure to animals and plant poisons. So it sort of the kits need to be designed around the complexity of the work environment for whatever that truck is exposed to. Again, emergency phone numbers should be posted in the truck. If you're dealing with chemicals, make sure that you have Chemtrack, that sort of number posted, that you have poison control number in your truck, obviously 911, your employer's main numbers so that everyone can get in contact with the owner or the person in charge back at the company, and maybe even the location of your designated workers' comp hospital or something like that. All crew members should be trained in emergency response and aerial rescue. Does this mean that each person on your crew has to be able to provide aerial rescue? No, it does not. What it means is that everyone has a role to play. You might not be the one climbing up the tree to rescue an injured climber or a climber that's been stuck in the tree. You might be the guy at the end of the street who's calling 911 and waiting there for the truck to show up. So it's important for everyone to sort of be trained. Also, emergency response could be everyone needs to know where the first aid bag is on the truck. Or maybe your company policy is to pull the emergency bag out and set it on a tarp somewhere in the work site so that you have it close by. All climbers, however, should be trained and capable of carrying out an aerial rescue. And, just like everything, practice is so important. We highly recommend quarterly training seminars for all the climbers to work on things like aerial rescue. And if you're using a bucket truck, make sure you're training with bucket trucks if that's all you do. If you're using these new like spider lifts and things like that, make sure everyone knows how to operate those things safely in a rescue environment. And if you have climbers that are on the more common rope and saddle sort of thing, how do you get up there and rescue those people? The more you practice that, the more you'll be capable of actually performing it under duress. A second climber that maintains line of sight with the aloft climber should be there to carry out an aerial rescue. So traffic control, this is sort of a big pain. Provide a means of control over vehicles and pedestrian traffic on your job site. It is the legal responsibility of the work crew to provide a secure work zone to ensure that no vehicles or pedestrians pass under trees in which work is in progress. If you've ever worked on a tree crew before, you know that no matter how many cones you set up, you can put out caution tape and all this other stuff. There'll be some guy who's walking down the road, just picks it up and walks right through the middle of your job site. It is your responsibility. Even if you put up all of this stuff and they go underneath and walk into your job site and get hit by a falling branch, it is still the tree company's responsibility. You're going to be held liable for it. So let your guys know to really enforce this, even if you have to get indignant with somebody. Obviously start off nice, but if you have to get upset with somebody, make sure that they don't get into your work site. A lot of people will actually go the extra step and they'll hire a company to come out and do that for you. They'll come out and do the traffic control. There's also certification classes that you can take for traffic control that you might want to send your guys to, depending on the size of your company, so that you have someone who is very well trained in traffic control. I'll talk about electrical hazards a little bit here. An electrical conductor is any overhead or underground electrical device, including wires, cables, lines, and related components and facilities capable of carrying current. So like even I have here in my neighborhood, it's underground utilities, but we have the metal boxes, every so many houses that are the transformers. Those metal boxes are metal and they are part of the electrical components. So these things should be considered an electrical conductor. An electrical hazard exists when a tree worker or any conductive object comes within the minimum approach distance in feet of an energized conductor. The absolute minimum is 10 feet. So the higher the voltage of the designated area is, the MAD increases. The big giant conductors out there might be 30 something feet. However, your regular residential stuff is going to be 10 feet. Direct contact means that a part of your body has directly contacted an energized conductor. So you reached over and you grabbed a power line with your hand or something like that. Indirect contact means that your body is holding something else that is conductive, and whatever that is touching an energized conductor. So you might be doing your 3-step cut and you reach out, and after you've made your first 2 cuts, you reach out to snap that branch off and it's heavier than you thought and it pulls you down and there's an energized conductor under you and it touches that. That is indirect contact. Or if you're using a stick saw and your stick saw gets pinched in the cut and it breaks off and it starts pulling it out of your hand, if you hold on to the stick saw as it touches an energized conductor, that is indirect contact. So PPEs, again, standard, this is chainsaw use, work boots, hard hat, hearing protection, eye protection, and saw chaps when working on the ground. You must understand reactive forces of the chainsaw. You know that every force has an equal and opposite force that's applied to get it to, once you put a body in motion, it continues in motion until you stop it in the absence of friction. So we'll show a little of that here in just a minute, so we'll come back to reactive forces, but it's very important to understand what those are. Control the saw shall use 2 hands, so all ground operations of the chainsaw shall require 2 hands. That's the way the safety mechanism is designed for that saw. Beware of those around you. We tend to get in a zone when we're operating something loud and heavy and takes a lot of our focus. We might get so hyper-focused of what we're doing that we forget about the people around us. And not only the people around us, but the other reactive forces in the brush pile. So we'll talk about that a little bit too. When you're going to walk from place to place with a running chainsaw, make sure that you are engaging the chain brake before taking over 2 steps. Another good idea on modern saws, we have all this compression release and they're much easier to start now. So you can actually just turn off the saw and walk from place to place and restart it when you get there. Or a lot of us now are transitioning over to electric equipment. And at some point, I guess our safety standards will catch up to what the industry is providing us. But obviously, if it's electric, it's only on when you've got the trigger on. So not the same sort of stuff for the electric. So these reactive forces of the chainsaw, the biggest one that we talk about is kickback. Kickback occurs many times faster than a human can react. And we'll look at it when I get the drawing of a chainsaw up, and I'll show you a little more about how that works. So chainsaws require no license to operate, no training for a residential person to operate. Remember, a tree care, someone participating in tree care does have to be trained by the employer to operate that chainsaw, and it has to be documented first. However, in general, chainsaws require no training to own or operate. There's approximately 28,000 people injured or killed every year as reported. So there might be more than this that goes unreported. And you know, our industry is quite dangerous. And so chainsaws used to be one of the number one or number two objects that injured tree care workers. Because of how safe these things are becoming, or because of the engineering that goes into chainsaws and chains and stuff now, that has dropped down a bit. Our number one cause of injury or death is falling, so falling out of the tree. Number two is struck by. So this is people that were in the drop zone of a branch. Or, you know, we also talk about widowmakers from time to time when there's a big dead broken branch in the tree and no one notices it. You start climbing the tree and moving the tree around, and then suddenly this thing falls and strikes you and could kill you. Number three is electrocution. Someone violated the minimum approach distance and made contact through a conductive tool or object. All right, so here's kickback. Chainsaws, they sort of run on the top side of this part of the chainsaw is called the bar. So on the top side of the bar, the chain is going away from the chainsaw. On the bottom side of the bar, the chain is coming towards the actual saw body. Right at this very tip, at some point on that tip, there is a change of force. You have something pushing away and something pulling towards, and there's one place right there on the tip where those two forces balance out with each other. And so if you touch the tip of the saw right there, you get it right at that specific point, what's going to happen is that you're going to have a transfer of that away force is going to be pushed onto an external object. So here, so as that tip touches, this is like you're trying to solve this, and this might be a smaller branch adjacent to it. And so as you're sawing through, this tip might come down and touch right at that specific point. And as it does that, you're going to have a transfer of force. The chain is going to stop, and then the force is going to be transferred to that tip, and it's going to throw back. So it's going to kick back at you. And if you're holding the saw properly, you've got one hand here and you have another hand up on top adjacent to the chain brake. This thing is going to pivot. It's going to pivot in this hand, and then that chain brake will catch up here, and it'll, you know, as the saw rotates around, it's going to hit the back of your arm and stop the chain from turning. Because as soon as that kickback happens, the chain starts turning again. So to the naked eye, the chain never really stops turning, but there is a point in there where it instantaneously changes. So that point out there, that's what you need to watch out for. That's where kickback is going to happen. So, you know, how can that happen? You can start like these plunge cuts. If you know how to do a plunge cut properly, you're going to know that you're just slightly on top of the nodes of this bar, so that you're still in that pushing away area and you're not where that force transfers. So you're going to put it in here just a little bit, and then maybe work your saw in. And then after you have the tip of the saw in, you can flatten it out a bit, because once the tip of the saw ends, there's nowhere for it to kick back to. It's just going to stay inside of the cut. As you're going through a stump where the stump is much larger, or even the trunk of the tree where it's larger than your bar is long, you could run into this situation. So as I'm moving around out here trying to work this cut around, I might bump that tip and this might come flying out. So if I'm working on a stump where I might have one knee on the ground and one foot on the ground in kind of an awkward position, and I'm trying to work it around like that, this is not where you want to. Make sure that you're still in a position of safety, that chain brake can come in and stop if kickback does occur. It can jump all the way out of that stump and get you. Talk about felling safety here. Workers not directly involved in felling a tree should be at least 2 tree lengths away. So if you have a tree that's 10 feet tall, make sure that you're 20 feet away if you're not involved in any part of the felling operation. Workers directly involved in the tree, but not the operator, shall be 1.5 feet away. 1.5 times, or 1.5 tree lengths away from the tree. So if you're maybe running a tag line up on top of a tree, you don't want to be 10 feet away pulling at the top of a 10-foot tree, because if you do, you're going to get smacked. So if you're 15 feet away and it comes over, when it lands all the way, it's going to be 5 feet in front of you. And if you have brush that pops off of it and shoots away at 1.5 times the distance away, you're probably going to be safe from other debris. The operator and everyone involved needs to have an escape route if something goes wrong. I'm sure you've all seen that YouTube video where the forester's out there cutting on the giant redwood, and the redwood starts to shake a little bit. He knows something's going wrong. He abandons that saw and tries to run like all heck to get out of there, and then that tree winds up just falling apart on him. But he had a predetermined escape route, and so the guy sort of got away safely. But holy smokes, that's a scary video if you haven't seen it. So the escape route is usually a 45-degree angle away from the line of fall. Well, you might not always know the direct line of fall. So your escape route might be an area that you have to plan to get to depending on how the tree falls. This one was sort of felling in the proper direction. I'm assuming that's the direction he wanted it to go. And so his standard escape route would have been 45-degree angle away from it. So a tag line that I mentioned just a second ago, so a tag line or a pole line, this is a static line that's attached to a branch or the top of a tree, but it's static. It's not going over anything. It's not a rope that has 2 ends to it. So one end of it's statically attached to something and you're just pulling on it. Retreat path, again, this is the one, your escape route that you're trying to get. So retreat path or escape route are the same thing. Felling notches and back cuts must be made high enough above ground level to enable the chainsaw operator to cut safely with a stable stance. And this changes as you age. When I started in the industry in my early 20s, it was no problem to get pretty darn close to the ground, make my cuts, and still have lots of flexibility to get away. Now that I'm almost 60, it's much more difficult to get up for much more than just sort of the standard sports stance where you have your knees slightly bent and shoulder width apart and that sort of thing, and I can still sort of run away from that. So it's left up to you on just how high that has to be. There are a number of notch types now. The notch is what you're going to cut out to control the fall of the tree. It helps us gain some aim, direction, and predictability to the fall of the tree. There's lots of these out there now for the guys that have been in business for a long time. I'm sure you've seen all the different kinds of notches out there. Our exam's really just going to focus on 3. That's the open face notch, the conventional notch, and the Humboldt notch. So these benefits of each, again, these things, especially if you've never been on a tree care work site, I encourage you to either go and work with a tree care company so that you can see these things in action, or for you to go to YouTube and start watching some YouTube videos from credible sites. There's a number of credible sites out there, but there's also a bunch of guys just sort of cowboying it that don't necessarily have great videos. So make sure that you're looking these things up, maybe from a manufacturer. I think Steel has some good videos on notches, as well as Husqvarna and a few of the others, where you can go and look at these things and see how they operate and why they operate the way they do. Keep in mind, this class is just sort of meant to be a refresher. It's meant for you to have already experienced these things, or to be aggressively seeking people out, or seeking experiences out where you're seeing these things in action. This class isn't meant to be sort of teaching you from the ground up. This should be something you take right before the exam. So please get out there and look and watch. Just to keep in mind, the thing that to recall here is that the open face notch, this one gives you the most control for the duration of the fall of the tree. So an open face notch just means that it's going to have a wider angle like this, and it's going to allow control when you make your back cut. It'll allow you control over the whole closure. In fact, the open face notch will never really close all the way to the ground, whereas a conventional notch is only 45 degrees. So on 45 degrees, that might just be like this, not 90 degrees all the way to the ground. It's going to be somewhere, it's going to be about halfway. So it'll go to this point, fall, and then pop off. So you lose control of it after the first 45 degrees of fall. You're going to lose control of it. But with an open face notch, as it comes down, you're going to hold on to that control, that sort of steerage. An open face notch is 70 degrees or more, and I talked about holding on as it closes. So, and when popping off, so that you're going to leave a little section of wood between the back cut and the notch that you put in the tree, that distance in between there, that's called the hinge wood. The hinge is what allows you to have control of direction and speed of the fall. Barber chair results when the trunk is split upward from the back cut. Going back to that guy's video, if hopefully you've seen it, the forester who's making that cut, as they're cutting into the back side, there's some tension on the back side, so it begins to split upwards like this. So if this is the trunk and your guy's making the cut here, it can split like this before the tree even begins to fall. So this happens a lot when a tree is leaning. So if you think about the forces of a tree leaning, you have one side of the tree that's being compressed and the other side of the tree that's being stretched. So you have tension wood on top, compression wood on the bottom. And if you look through that, if you look at the forces applied to that trunk as you go through the trunk of the tree, there's some point inside of the trunk, it's going to go from a stretching force to a compressing force as you cut through it. And so there'll be a line. We refer to that as a shear line. So as you're cutting from the back, at some point that tension is just going to give way and the compression is going to stay. So that's another example of how barber chair occurs. Barber chair occurs really quickly, and that piece can come up and hit the operator in the face. It can be quite painful. It could kill you if the tree is big enough. How do you prevent this sort of thing? It's a typical question that I get from the gallery. Everything from, strapping. So you can put straps onto the trunk of the tree and ratchet it down nice and tight. If your tree is big enough, you might even want to use chain with a big binder on it, so that it'll prevent that. So even if it does split, it's not going to go anywhere. It's not going to hit the operator. Felling wedges, these are very useful when making the back cut. If you have a tree that is straight up and down, the canopy's perfectly balanced, and you cut this notch in one side and you're cutting your back side, well, where's the actual force of the tree? It's still straight down. So you need something there extra to encourage the tree to go in the direction of the notch, and that's what felling wedges do. So as you're cutting through the backside, you might put in these wedges, and then you're smacking the wedge with a hammer or a sledgehammer or something like that to drive them in. And so that's like an inclined plane. It's one of the oldest tools that man has in order to move things. So as you're driving this in, it can tilt the tree just enough to encourage it to go in the direction that you want it to go. That can also prevent the problem of setting back. So as you're making your back cut, maybe the canopy's balanced a little heavier on the side of the back cut. And so the tree's going to want to sit down in the direction that the operator is. If it does that, it's going to pinch the chain. And so you pinch the chain, the saw stops. And if it's a big tree, you're not getting the saw out of there until the tree falls. So a way to prevent that is, as you're going in, maybe drive wedges in behind the chainsaw. And because of this, you're going to want to use a soft plastic or a soft aluminum wedge, something that is a softer material than the chain, so that you're not tearing your chain up. So a standard or common notch is a 45-degree opening with the cut above the horizontal cut. So it's, it's 45 degrees. It's like this. This one's horizontal bed cut. Here's the opening face cut. It's 45 degrees. The Humboldt cut is a 45-degree opening with the cutout below the horizontal cut. So here's the standard. Flip it upside down like that, and that becomes the Humboldt. The Humboldt's typically used in forestry where where the final cut is a wood round, basically. Open face is now the most commonly used notch. The notch cutout is again about 70 degrees. This notch has the greatest amount of control. Holding wood should be at least 10% of the tree's DBH. So if you have a tree that's 10 inches in diameter, you want that holding wood. Again, the holding wood is the same as the hinge wood. So you want the thickness of that hinge wood to be 10% of the tree DBH, or you want it to be 1 inch. So you want 1 inch of this holding wood between the apex of the felling notch and of the face notch and the back cut. So you want about an inch, at least an inch apart there. Back cut should be made an inch or two above the apex of the cut, back point of the notch where the top and bottom meets. So in our common notch, here you've got the flat horizontal bed cut, and you've got the 45-degree cut at the top. Where those two intersect at the bottom, that is considered the apex of the cut. Brush chippers are very dangerous, and they require proper training and safe work practices. These things are just super dangerous. Proper PPEs, such as no loose clothing, no jewelry, no climbing saddles, no harnesses or body belts, and/or gauntlet type gloves should be operated anywhere around the brush or the chipper. Aerial lift operators must be properly trained on inspection, how to inspect your vehicle every day, maybe even between trees. Every time you break it down and set it back up again, it should be inspected partially, at least. A full inspection at every daily use. Make sure that you have the appropriate PPEs, the appropriate fall protection that goes with your type of lift. And people need to be trained, as well as the operator, on emergency lowering procedures. How do you get this thing down if the battery dies, or you run out of gas in the pony motor, or you're on such an angle that after you're up there and working, the oil sensor shuts everything down. You need to be able to get your person out of the bucket if they die, if the machine dies. Be familiar with the capabilities and limitations of your equipment. There's lots of different configurations. There's rear mounted and front mounted bucket trucks. There's elevating bucket trucks, as well as those with the arms that come out and do different things. We have now we have these other aerial lifts that are self-powered, like the spider lift and things like that. So be familiar with what angles these things can sit on, what their limitation is. You don't want to exceed their limitations. So now we're going to just quick have a slide on palm safety. So whenever you're taking or pruning palms, remember you want to do them from the top downwards. The hazard here is that sloughing of the palm skirts. So palm branches can actually break off and just sit on other palm branches. And you might not know that they're detached because of how they decay and separate close to the trunk. So you could be, if you're under it, you're pruning off, suddenly you could have not just the one that you're pruning off, but you could have a couple of 100 pounds that might be laying on it, just land in your lap as a climber. Never a fun thing. Watch out for potential hazards to targets below. When you're climbing a palm tree, maybe shake out a coconut. Think about a coconut in a parking lot. And this coconut could fall to the ground and land on a worker. It could land on a car. It could land on a home, as well as, the palm fronds and stuff like that. So there's nothing pleasant about a palm tree, especially if you're a climber. Avoid climbing and working under the hanging palm fronds. Again, we want to work them from the top down. So the best way to do it would be from a bucket truck. It can be quite difficult to access the top of a palm tree unless you have a bucket truck. Sharp palm fronds, the edges of them can be quite sharp, and if you have enough load, if you've got 200 pounds on your climbing line and one of these things breaks loose and rubs up against your climbing line, it can cut it. So be cognizant of that. And the other danger is from nesting animals and insects. I've had everything I can imagine crawl out of palm trees when I've been working on them, from snakes to possums to frogs to just everything you can imagine. These, the palmetto bugs, the giant cockroaches that jump out and start crawling all over you. None of that is fun. Okay, any questions here?
So far, I don't have any in the chat or in the Q&A. Anybody got anything for Rob before we move along? Been a very quiet group, Rob.
It has been.
Oddly.
I wonder if they're even around, it's like it's, when we used to use that other, let me see here, I've got to get back to, when we used to use that other format before we were using Zoom, it would tell you if people were looking at their screens or not.
Oh, y'all better start asking some questions. I'm going to be implementing that very soon. I got some people, they say they're here.
Okay, so we're going on to what, 16 now, right? So you are still seeing the...
Yeah, right now I still have chapter 15.
All right.
There it is.
Okay, so which one are you looking at here?
Go ahead and go up to slideshow, far right. Right there, yeah. Let's see here. All right, swap your displays.
Maybe it'll work this time. Last time when I did it, I got half and half.
Well, this is perfect. Thank you.
Okay. So we're going to jump right into this sort of climbing and working in trees section. See, where am I? It took about an hour. So, all right. So climbing and working in trees. We're just going to get going with it. This is chapter 16. We'll talk about the standards and safety regulations, safety equipment, ropes, knots, tools, tree climbing techniques, and safety hazards. We'll get into the principles of rigging equipment and technique, and emergency response procedures. Again, I cannot emphasize enough, if you are not involved in daily tree care operations, if you are taking this exam because you have the right number of college credits and you've worked in the front office or something like that, and you've never seen these things, it's going to be difficult concepts to understand. So I encourage you to go out with crews and watch crews as they do their jobs. I encourage you to watch videos to see how professionals are doing these things. Again, look for professionally produced videos that might be sanctioned by ISA or TCIA. So look for these things. Just because a climber looks cool doesn't mean that he knows what he's doing or he's implementing all the right safety practices. So, here we can see that our operator is operating his chainsaw with one hand. He's got one hand up here. He's sawing towards his leg. His safety lanyard's just laying, it's over the tree over here and laying straight down over here. His feet are dangling. So, it doesn't look like he has on his eye protection. It's hard to tell. So just because you have on, nice equipment, fancy stuff, doesn't necessarily mean that everything's there. Here's our standard guy. And I hope at the end of that, I took some pictures the other day of Jimmy Pritchard. So I hope to be able to show you some of those at the very end. Hopefully I can pull some of those up and show you how far things have come in the decades that I've been in the business. But when I started, this was your pretty typical amount of safety gear. You've got your hard hat, your face shield, eye protection. You've got your non-gauntlet style gloves. You've got your chaps. You've got heavy duty work boots. You've got a chainsaw with all of its safety things in place. And you also have the muff style sort of hearing protection back there. So it's the normal stuff. Equipment should be inspected before each use. So the climbing equipment, the saddle will have all these points of attachment that put it together. They can be riveted and sewn. Some of them are metal reinforced, things like that. So make sure that you're looking for fraying, that you're looking for rivets that have come undone, that, make sure that you're looking at all of the extra little safety things or carriers on there to make sure that they're fully attached. Climbing saddles should be checked for excessive wear and see that the stitching and rivets are strong and intact. Snaps secure the climbing line or lanyard to a saddle. So a snap is going to have an eye on it. In our industry, you have to have self-closing and double locking on everything that supports you as a person. So here we have a gate, and there's a spring load inside of here. In order to even open this gate, however, we have another safety measure in here, so that's also spring loaded. So we'll have to compress this side, which will release this opening and then allow us to open the gate in order to be able to attach it to something. So this is a regulation snap for use in climbing. A climbing line or a lanyard must also remember anything that is supported, that's supporting your human, needs to be this self-closing, self-locking. So this end might attach to your saddle somewhere, might use a carabiner on this side. So this would be a snap, because again, it has that eye at the end. This is a steel core lanyard. So the steel comes out, goes around a permanent thimble, and is threaded itself back into this turnmental type of rope. I can attach this to my saddle by using a carabiner if I choose. I don't have to use a snap. This carabiner, this barrel right here, has to be pushed down, and it has to be rotated in order for this little U shape to line up in the front, allowing it to open. So again, this is self-locking and self-closing. So another way of self-locking is positive locking. So this is a carabiner. It does not have an eye in it. So this is not called a snap. This is a carabiner. No matter what you use, it must have the tensile strength of 5,000 pounds. Now, what is tensile strength? That is pulling. So in the direction that the forces go, it has to be 5,000 pounds. Now, if you ever get one of these carabiners, you'll notice that it has a couple of numbers on it. It'll have one in this direction, and it might have another in this direction. So you can, if it's oblong, if you're pulling on it like this, it's going to have a different tensile strength than pulling on it like this. So the minimum it can have in either direction is that of 5,000 pounds. A snap, you have no choice but to use it in the way that it was intended. These things can flop around and move, so they're not always on pulling straight on the carabiner. It might get sideways a little bit, and you might be pulling it apart in this direction and not this direction. So the top to bottom direction might be significantly higher than 5,000 pounds, but the one going in this direction will be 5,000. There's also metric equivalents of these things, so it might be handy to know what the metric equivalent is. It'll be identified in your book. The safety standards portion here, we use ANSI. The Europeans have a different standard that they use, so I think their standard shows up on their exams. But there are two different measurements. Like we have here, climbing lines must be at least 1/2 inch in diameter. Or if you were talking about the metric system, it's going to be 11 millimeters. And if you ever hold them in your hand, you're going to say 11 millimeters is smaller than 1/2 inch, and it is just by a hair. So this can be read as a minimum of 1/2 inch or a minimum of 11 millimeters. Your tensile strength of the rope is 5,400 pounds. Now, why do you think that it's higher than that of the hardware? Well, it's because when you tie a knot in a rope, you decrease its tensile strength. So this 400 pounds extra helps to account for the loss of tensile strength due to the knots that you have to tie in it. Work positioning lanyards are ropes or straps designed to aid in climbing and tree work or a secondary means of attachment. So this would be an example of a climbing lanyard. This would be an example of a tool lanyard, like a chainsaw, something like that. So this is, you would have this end attached to a chainsaw. This end would be attached to your saddle. And then if you're not using it, you might have two things clipped into this point of attachment. You come up, clip it on this ring, and it holds it a little closer to you so you can reach it. So rope comes in a variety of types and sizes. 3-strand rope, this stuff has relatively low strength. I'm not even sure you would see it anymore in the industry. It's relatively inexpensive. You know, if you ever go to the hardware store and you see that old hemp rope or something like natural fiber rope, that's probably going to be 3-strand rope. It's where 3 strands have been twisted with a bunch of other strands to form the rope. However, more typical in our industry now is this 16-strand rope. It has very good abrasion resist. You know, if you nick a couple of these strands, it's not going to be the end of the rope. Whereas in 3-strand, if you start to nick it away, it deteriorates in a hurry. Kern mantle rope means that it's a core and a cover. So the core over here is what's going to bear the majority of the force, and then it's covered by, so the core is covered by a cover, and this cover is really meant for abrasion resistance. This is the climbing line that I use. We refer to this as safety blue. The core inside of there actually has some blue thread that's woven into the core. So if you ever nick the cover to the point where you've damaged the actual structural integrity of the rope, it'll pull out a few of those blue fibers. So if you ever see that safety blue part of it, if it ever pops out, that's why it's there. It means the rope's no longer good. Use the correct type of rope for the application. And this really boils down to diameter. So if you're working with very large sections of wood, very heavy weights, you want to have rope that's appropriate for that size. So even though 1/2 inch might be what you use for a climbing line, if you're using relatively small stuff up in the tree, you might use 9mm rope or something for lowering if you're working on really small stuff. If you're working on really large stuff, you know, you could use 1.5-inch rope or bigger. None of which is fun the big stuff, definitely not fun to use. It's really heavy.
Rob,
Yes.
Andrew does have a question, and I think you actually may be getting to this here in a minute. Does tensile strength requirements change for dynamic versus static lines?
Yeah, so tensile strength is the load that the maximum load that something can endure without permanently deforming the rope. So it doesn't matter if I'm putting 5,000 pounds of direct pressure on the rope, like in a static line. If you're just pulling it, you know, like if you attach it to a truck or something and you're pulling on it, if you reach that 5,000, if you exceed that 5,000 pounds of tensile strength, you're going to permanently deform that rope. If you're dynamically loading the rope, which means that it's the experience of the rope changes constantly. You know, like if you're dropping a piece out and it goes from not having any weight on it to having a load on it to, to having to stop acceleration due to gravity. If you're having to stop that and then lower it, so that the maximum force that rope will experience cannot exceed 5,000 pounds. So it doesn't matter if you do it statically or if you do it dynamically, can't exceed 5,000 pounds. So you might have to calculate what 5,000 pounds of pressure looks like dynamically, but you cannot exceed it if that's the factor of your rope. Hopefully that answers his question there.
Awesome. Thank you. Let me know if you have any other questions, Andrew.
So, again, the tensile strength is the maximum load the rope will support. This doesn't necessarily mean the rope's going to break. It means you're going to stretch the rope and it won't go back to where it was before. Ropes are designed to be able to stretch a little bit, but they have to go back to where they were before. A design factor, this is the safety factor for arborist rigging, and it should be a factor of 10 or greater. And, we take our working load limit and divide it by the design factor, and that will give us the tensile strength. Or another way to look at it is our working load limit should be sort of 10% below the tensile strength. Knots. So Knot is a general term for hitches and bends. So this is sort of the umbrella terminology here would be a knot. We can break knots down into hitches and bends. So a hitch is a type of knot used to secure a rope to an object or another rope, or the standing part of the same rope, such as our climbing hitches. A bend, this joins two rope ends together. Like a sheep bend, we can also have like a clove hitch, as you see over in these pictures. You know, as I learned last week, I went out with Jimmy Pritchard, as I was saying earlier, and I learned about modern climbing techniques. So there are really two types of climbing techniques now. We have SRT, which is stationary rope technique, and then we have the moving rope technique, MRT. So it used to be single rope technique, but they just changed single to stationary so that it's easier for a climber to envision whether both ends of the rope are moving, which is a moving, or if the actual rope remains static and you're just climbing a static line that does not move. So SRT and MRT, those might show up on an exam. And I've also learned that most climbers now don't even use hitches at all. They use mechanical devices that behave as a hitch. But we're going to learn about how these things work, because the actual mechanics behind whether you're using a mechanical device to climb on the line with, or if you're using a hitch to climb with, the principle is the same. So the Prusik loop is a loop of rope that's put through itself a couple times. So notice there's 4 turns on the rope here, starting on the outside, going inward. As I pull on this, if I pulled on this end, these loops are going to tighten around the static line here. This is the line we're going to ascend on. So if I'm doing this, if I'm putting pressure on there, this rope's not going to move relative to this one. One's going to be held via friction to the other one. If this end is attached to my body weight, as an example, or let's take a look at this one at the split tail system. So here's this little piece. This is attached to my climbing saddle. This piece is attached to the rope, and this looks like probably a Blake's hitch or something like that. This little short piece gets weight on it. It tightens up this line and holds the climber to the climbing line. So if he did not have any hands on it, if you just took your hands off, and just laid back, that hitch is gonna hold you. So if I take the line and I pull down on the line and I push up on the hitch, after I get some sort of slack in this standing part, it loosens up and I'm able to advance it up the line. The split tail system allows you to put in a little pulley here. So as I pull on this hand with this line, this pulley is going to go up and touch the back end of this knot and advance it up the line. So that's how you're going to climb on the split tail. Here's some other examples of some hitches. This is a taut line hitch. So here you're going to pull down on this line, and then this line that your body's attached to is going to go up the tree. Or if I loosen this and I allow rope to run in this direction, this side of the line is going to come down and lower me out of the tree. So this works in both directions, but this is an MRT. This is the moving rope technique. This is the sort of the progenitor of all of these different hitches and pieces of equipment that we use today. The Blake's hitch doesn't get quite as bound up. It's easier to use. You don't have to like loosen it up throughout the day nearly as much as you would the taut line hitch. So if anything, the taut line hitch is going to be a tighter, there's going to be less slide, less everything. It's just going to stay where you put it after you use it a few times. Whereas the Blake's hitch sort of maintains the same amount of friction throughout the tree. Prusik hitch works very much like a taut line hitch. It's just a separate piece of rope, it's just a loop. So you're running that loop inside of itself around the rope a couple times to get that. And here's an example of a bowline. This is a static bowline. It's just got the loop in it. Again, here's the climber. So notice this guy, he might have been doing some foot lock. He's using the split tailed technique. There's just one line here. You don't see the other line. So this is a static rope technique or a stationary rope type of technique. However, as I learned, all of this is still very old school. So now we replace these hitches with more mechanical devices. You might have a knee ascender and a foot ascender over here, and you simply just walk up the tree it's even easier than walking up a ladder. It's pretty incredible how these things work now. But it all has to do with tension on the rope. So whatever tension you're placing on, like the green line here is the climbing line, this red line is what's holding you on, whether this is a prusik loop or a hitch of some type. So again, when you push up on the bottom of it, that loosens these coils and makes it easily move. When you're putting weight down on this part of it, that's what binds the knot up and holds you in place. So these are friction knots. Here's some examples of some other knots that are out there. Just sort of read over the notches. Read over the knots in your book. Whenever you see them in there, go and look them up. Watch people tie them so that you have a better understanding. Get yourself about a 6 or 7 foot section of rope and practice these different knots and hitches. There's just all kinds of terminology that goes with them, but remember that most of what you're going to see in the general presentation here is what's going to be on the exam, but it gets much more in depth. You can have the distal hitch, the Swabish hitch, the Valtane switch hitch, the Blake's hitch, the taut line hitch. So there's lots of these things, even in the prusik loops. There's the climb heist, the prusik 4-coil, the prusik 6-coil. Again, the Valtane. There's all kinds of these knots out there, so don't get too caught up in them. Just sort of know what the common ones are, how they tie, and how they work. What's the principle behind why you're using each one of these? So how do you actually get into a tree? Or how do you get your climbing line? Because we all know you don't use climbing spikes in a live tree that you're pruning. So you want to get your climbing line into the tree. To get that up there, you might use a throw line. So this is an example. This is a bag that's going to hold your line. This yellow stuff is the throw line. This is the weighted bag that you're going to use to launch up into the tree. So you're going to take this little bag, you're going to throw it. It goes up and over a branch and comes back down. You tie your climbing line off to this stuff, and then you pull it on through the tree, and that's how you get your rope up in the tree. So it's just keep in mind that a throw line is a combination of this line and the weighted bag. So there's 2 main techniques for actually ascending your body up into the tree. One is the body thrust, and this is used mainly on the moving rope technique. And then there's foot lock and variations of the foot lock, such as the foot lock in the knee, the foot ascender and the knee ascenders combined. So in the picture over here, you can see that he has a foot ascender over here, and this foot is attached to something he's going to advance by his hand. Even more modern than this now is one that's sort of a stiff line that attaches to the knee over here that keeps this going. So, but they all sort of work the same way. There's a little cam in here that when you put weight on it, the cam closes and holds the rope in position. So when he steps down with this foot, he's pulling that line through his harness, and he's going up the tree. So they're called ascenders because they only work in one direction, and that's as you go up. Climbing spurs or ladders are another way to get into a tree. Climbing spurs are often used, or should only be used, in 2 conditions. One is an aerial rescue, and 2 is a tree removal. There are some circumstances where climbing the tree without a direct point of attachment above you is just far too dangerous. And so in very limited circumstances, climbing spurs may be worn to prune, but only until you get to sections where it's easier to do it, or it's safer to do it with a rope than it is with the climbing spurs. But in general, aerial rescue and tree removals are the only time you use climbing spurs. So cutting tools, you should have very clean cutting tools, sterile cutting tools. You should be cleaning these things between each job site. You should make sure that you're using current technology because it's going to make a much smoother cut. You're going to have all your pruners. Notice all these pruners are bypass pruners. None of these are anvil style. These are the new style, or not, it's not even new anymore, but the Japanese style of teeth that cuts on both sides in both directions. So they're mainly meant to cut when you pull, but it cleans the teeth as you make that pull stroke. So it's cutting and cleaning in the same stroke. Yeah, so basic cutting tools. So rigging. Rigging is the use of ropes and other equipment to take down trees or remove limbs. So again, keep in mind, rigging is whenever you're using a rope in a tree, other than your personal climbing line. A rigging point is the place in the tree that the load line passes through to control limb removal. Again, try to find some YouTube stuff. If I have a branch and my line comes from one side, if I'm holding one side and I throw my rope over the other side, and I'm going to have some weight on both sides of the rope, this tree, this branch up here, this is the rigging point. So I'm doing everything from this rigging point. So in the example I just gave, that is a natural crotch. It uses the branch attachment points or crotches of the tree for that rigging point. However, if I'm going to use the same rigging point over and over and over again, my rope, as the friction goes over it, might wear through the bark and into the cambium and damage the cambium. So on thin bark trees or trees where you're going to run the rope a lot, you're going to want to employ the use of a false crotch. So I'm going to take maybe a block or something, or a block or a ring or something like that, and put it on over that rigging, the natural rigging point, and then I'd run the rope through whatever that pulley or ring or whatever I'm going to use is, and that makes it a false crotch. So you have a natural crotch and a false crotch. So again, it all comes down to friction. The more friction you apply to something, the faster it stops. So brakes on your vehicle as you're driving down the road and you push down on the brake pedal, forward momentum. So that's how friction works. So on the example here, this is a lowering device. This is a very nice one. This one also place. This rope is going to go up, and this is what's going to bear the main part of the weight. It goes through this little guide, and then the number of wraps that we put on this capstan, every wrap has some amount of friction. So the more wraps I add to it, the more friction is transferred to the capstan. And so I can have one operator over here hold up, the better part of 1,000 pounds with one hand between his thumb and his forefinger, if they have the right number of wraps on here. So in rigging, you're usually taking something out of the tree. So you've got some big log and it's tied onto a rope, and then you're going to lower this log to the ground. Well, as the weight transfers, we talked about the dynamic load of a rope. So as the load transfers from one place to another, and we'll have an example of it in a minute, but as it does that, it's going to pull down on that rope. If the rope didn't move at all that load's going to be transferred onto the rope. And as it's transferred onto the rope, it'll be transferred to the rigging point, which is going to pull the tree over. So if you have a climber up here and you pull the tree over when it falls, you might risk, knocking your climber out of the tree. So you really don't want to just stop it. So as the piece falls over, you want to be able to let it run a little bit. So you don't want to put so many wraps on here that with no pressure on the rope that stops it from moving. So you want the piece to be able to move. And this is going to come about from practice, from using it. It's not something you're just going to know instantly. Hopefully your climber was a groundman for a long time and ran ropes before he became a climber. So the climber, when you're starting off, is going to tell you, say, put 2 wraps on that, put 3 wraps on that, or he'll give you some indication that'll get you close to what's necessary. A shackle is a U-shaped fitting with a pin run through it. We'll look at that in a second. Screw links are connecting devices with a threaded closure mechanism. And, it looks like a regular chain, except one of the links has a little gate on it that you can unscrew. This is another type of friction device. Didn't mention this is called a porter wrap. It's very common in the industry. It's much smaller. It's designed to handle smaller loads and to be set up in multiple places so that you can move this quite quickly. This one you might use when you're taking down the tree in general because you're going to use the same device throughout the whole removal. This one you might move around from place to place or point of attachment. You could even use these up in the tree. A block is a pulley used in rigging, so this would be a block. A sheave is the inner fitting of the pulley, so that's what's going through the center piece in there. A rope sling is a section of rope, usually with at least one eye splice, used to secure equipment or tree sections in a rigging operation. So here's an example of a sling. So you have a loop, and this is woven back into itself for good strength, so you're not losing a whole lot of tensile strength here because of how this is spliced back into itself. And then you have this long tail, so it's a loop and a tail. We'll see sort of how that's used in a minute. So here we have that sling, so our rope sling right here. So here's the end with the loop in it. The loop's going to go into this block, so I'm going to pull that sheave out of there and pull the little round piece out, put the rope in, put the block back. Put the pulley back, put the sheave back, put it in place, and it's locked, it's screwed in, it's bolted into that eyepiece. And then the long tail, I'm going to wrap around the tree, come back, wrap around just above the rigging point, and then loop it around the tree a few times until I run out of tail. And that's called the timber hitch. And so you're not even actually tying a knot. You're just sort of putting so much friction on the rope that it can't come loose or move. Here's an example of a clove hitch. Tying at clove hitches are fairly common. We showed that bowline a while ago. So remember, it was just tied onto another rope. Well, here it is. The inside of the loop is the rope itself. And so this becomes a running bowline. So we could stand on the ground any distance away. So we throw our rope over, bring it down. We're holding both ends of the rope. And then we take one end, loop it around the other end of the rope, and then tie a bowline in it. So we've got our bowline looped around the other end of the rope, pull down on this rope, and then this whole knot runs up the tree, hence the name running bowline. So rigging techniques. So this butt hitching. This is where that dynamic loading is really going to come into play. So butt hitching is a method of lowering a piece when the rigging point is below where you're tied in. So you're taking out something above your head. And so if you have a big log and you've got your climbing spurs on, you've got your lanyard on, you've got your climbing line, so tied on, you've got the log above you, and you have a rigging point. So you've got like 3 sets of rope in front of you, trying to juggle all this stuff and keep it together. But you have this piece that's your head is looking at the butt end of the log, and you've got some distance, whether it's 2 feet or 8 feet above your head. The rigging point is right in front of you. So here's the butt end of the log. The rigging point is below that. So when the log falls over, for some distance after you cut it, when it's falling for some distance, it's going to be subject to gravity. And gravity is 9.8 meters per second squared, or 32 feet per second. So as it's falling over, it's accelerating. So the further it falls, the more speed it collects. And force is directly related to mass times acceleration, m times e. So the further it falls, the more acceleration, and whatever mass it is accelerates to whatever speed it gets to, and you can calculate what the maximum dynamic load is going to be if you just stopped it. If it just falls into the rigging point, that's going to be the maximum dynamic load that rigging point sees or that the rope experiences. Now, if you have a good rope operator and he's not stopping it, you can control the amount of dynamic load. And so by letting it run a little bit and slowly stopping it, you can change what the maximum load is. When the piece is falling free fall, if you have a good ground operator that can take up the slack and actually keep it pulled into the rigging point. So if you have, you know, a foot and a half here and a foot and a half below where you're doing it, instead of having a 3-foot fall, if he's sucking it up, you might only have a 2-foot fall or a foot and a half fall, which cuts the acceleration time in half. And remember, it's squaring. So if you cut the time in half, you're actually exponentially lowering the dynamic load experienced at the rigging point. So hopefully you sort of understand what dynamic loading is. If not, again, go to YouTube, look it up on a reliable source and watch it a few times. So butt hitching is where it starts off above you and falls, and you've got all this dynamic load. If it's attached to a line, which it is because you're butt hitching it, once it comes over, you're going to want to lower it down to the ground. And so you're going to have a landing zone. Remember, think of like an airport, a controlled descent. So your landing zone, if you had no rope on it, it's going to be your drop zone. This guy has his porter wrap attached to his vehicle, which you're not supposed to do, but porter wrap's attached over here. The rope's coming in. Notice this guy's, it's the same operator. So it's going through his friction device up to some rigging point and back down with the load on it. He's handling it easily with one hand and setting it down on his landing zone. Here's some more advanced techniques. One's called a speed line. So here you can have this rope would be going towards your chipper. This line itself, the green one here would be static. So it's tied off at some point up in the tree. This one might be tied off somewhere close to the chipper. And so you're going to attach a branch using a loop or a sling and a carabiner, and you might attach it to a rigging plate like this one, or you might even just attach it to the rope itself. So you cut it and it runs down like a speed line all the way to your chipper. The tighter this rope is, and the greater the angle, the faster it's going to go. And so in order to stop it, your operator on the other end of this back towards the chipper might let in a little slack. And as he lets in slack, the rope does like this and it slows the piece down. So the piece actually lands on the ground before it gets to the chipper. So if you have a really good operator, you might find somebody that can come and land the butt end of that right on the chipper deck, put it right where you need it. But again, you're not going to start chipping it until you get all the hardware off. You might say, well, how do you get the sling back up into the tree for the climber to use on the next one? Well, you have this, in this example, you've got a little pulley system here with a rigging plate on it. You've got this purple line, which is the return line. And you can see that I have 2 other openings on here. So if I was working with little branches like this, I might put 3 or 4 or 5 branches attached to this rigging plate and let them all down at one time. All right. So here we go, into this section now. Do we have questions there?
As of right now, I have no questions whatsoever.
Okay. Well, so we have a break right now, is that right?
Yep. We are taking a break. Everybody come back at 10:50. 10:50. And of course, I'll give my normal shout out to y'all, okay? So go take your break.
All right. See
Thank
you guys back in a minute. Yep. So Brittany, are you around?
Yes, sir. I'm right here.
So can you see my screen right now?
I can. I'm seeing a picture.
All right. So guess I just wanted to, for anybody that's hanging around and watching, I just wanted to show some of these pictures of Jimmy Pritchard before we get on to the next section. So
That sounds great. Awesome.
yeah, so for those of you that are out there watching, I went up and watched my friend Jimmy Pritchard, and again, he's an international climbing champion. The thing I like about working with Jimmy is he's 51 years old. So if you think that you can age out of this as an occupation, as a climber, he's living proof that you can do it your whole life just about. So here's his gear bag. This is he has so much gear, he wheels it out on this cart looking thing. So there's the inside of his gear bag. This is the tree that we're assessing. It has a lot of very interesting damage all over it, and so I wanted an aerial view of it. So I asked Jimmy to go up and take a look. Here are his throw lines. So this sort of basket has the string in it, and then over to the side you see a little pocket with the weighted line. Here's another shot of his gear bag. See, I can blow some of this up so you can get a better look at it. Now I have to get it back. As I try to do it, my whole system locks up. Here we go. So here's Jimmy actually using the throw ball here. You can see this is the weight, and this is the line. We've got it set up into the tree. So this is the throw line he used, and this is his big climbing line going up into the tree. So that's going to go up, go through the rigging point, come back down. Now this is him tying on a climbing line. Again, going up, you can clearly see the throw line and his climbing line. This is just a look at his climbing line. This is 11 millimeters. So again, it's slightly smaller than the 1/2 inch that I use. Here's a picture of Jimmy. Looks a little different from that guy that we saw in the other safety video. His saddle's just loaded with stuff here. He's getting prepared to do a stationary line technique. He puts he puts this knot on one side, and then he's going to run this thing up into the tree. And that becomes static. Here's some of his climbing equipment. Notice all the stuff he has. So this is his friction device, and these are some other friction devices. He has like 4 or 5 different ones, and he says in some situations he's more comfortable using one over the other, but they're all really safe things. Here he is attaching this friction device to the rope. Again, this replaces that knot that we showed earlier. This piece holds it close to his chest, so it really doesn't bear any weight. This green rope is attached to his saddle on a sliding ring, so that he still has lots of maneuverability to twist and do things up in the tree. He's hooking it up to his foot ascender here. You can sort of see what it looks like there. And then here's a movie. See how it just looks like he's just climbing a ladder up into the tree. So his hands up here, we're just sort of taking up just sort of guiding him along. I'll play that again so you can see it. So it's a pretty neat technique. You can see him way up in the tree, sort of right there. He likes to wear bright orange so that he shows up. Here's a closer look at that friction device he was using. Notice we have a working load limit here of 130 kilograms, and there's little notes and stuff all over this device. There's the manufacturer. There's sort of a look at it, how it moves in that direction. Here's the opposite side of it, again, where it's explaining what the rope diameters are. 13 goes up to 13 millimeter, so 11 to 13 millimeter diameter. So that well covers 1/2 inch also. So this will work with both 11 and the 1/2 inch. There we have our Georgia arborist people.
Well, we're glad that you ended on us. I will say your friend looks very young. He does not look 51, so that's amazing.
Well, a lot of it has to do with genetics.
Yeah.
I don't think he's been above 8% body fat his entire life. So he is quite fit. But he started this, he worked for his father in high school. So he has been doing this since high school.
That's amazing. Well, guys, everybody, if you are in earshot and you didn't get to see Rob's pictures, just head on back. It looks like we're getting started here in about 2 minutes. Rob, if I am not able to come back on, I am still here. Just at the end, if I'm not able to come back on, you've got the Q&A to answer any questions that might come across, and I will still, of course, be dropping that CEU sign-in sheet at the end, and then I'll share my screen so everybody can see the confirmation that I've got your CEU sign-in.
Okay, so at the end, I'll stop my screen share so that yours can take over.
Yeah, you stop your screen share, but you have to make me host again. You know how you click on my
Yeah, I think so. Yeah.
Under participants and host, you just click on my name and make me the host again.
Okay.
So I can do that.
Will do.
Okay.
So let me see. What are you seeing now? Do I need to switch it around?
Your displays.
I need to switch it.
Yep.
Okay. Does this look like the right thing?
Yep. Perfecto.
All right. How about that? I negotiated slides and pictures and
Yeah. And Jeff says, don't mess up my instructions. This is the one time that I have like 30 minutes of multitasking, unfortunately. So sorry about that.
yeah, I'll try to let it run until it works, Jeff. So hopefully it'll.
Well, I'll still be here. So if there's problems, I'll pop right back on.
All right.
All right. Thanks.
You bet. All right. So it looks like we're at 9:50 or 10:50 there. So we are ready to go. Our last section here. This is tree assessment and risk management. And this is really just going to be an overview. There are more advanced courses that you can take. There is the tree risk assessment qualification. After you've been an arborist for a couple of years and you sort of feel like you've been experienced, you might want to take the TRAQ class, TRAQ, to learn a lot more about tree assessment and risk management. So this is really just an overview that a typical arborist is going to experience. It does get a lot more in depth than this. So we'll talk about the tree risk assessment sort of process, wood decay, the mitigation of tree risk, and the arborist's responsibility and duty once you become an ISA certified arborist, you're going to be held to a different standard than the rest of the untrained world. So be cognizant of that. Tree assessment and risk management are important roles of the professional arborist. Risk assessment is the process of evaluating the likelihood and the consequences thereof that a part of a tree or the entire tree is going to fail and cause damage or injury. So it doesn't necessarily even have to fall. We talked about it in the pruning section where the end of a long branch might be covering up a stop sign. That is part of a risk assessment. It's like, okay, the risk associated with this tree is that it might cause a vehicular accident because people aren't going to stop. They can't see the sign. What's the abatement? The abatement would be to prune the branch so that you can see the stop sign. What's the part that's at fault here? Well, it's the foliage at the end of the branch. What are the consequences? People run the stop sign. Will those consequences result in significant damage or injury? Car accidents most certainly can be that. So that has all the attributes that it needs to be a significant risk, if not going as far as to call it a hazard. There are 3 factors of the basic assessment. What is the potential for the tree or one of its parts to fail? What are the conditions that may contribute to that failure? And what is the target? What will be damaged or injured if it were to fail. So failure potential, this is the likelihood that an entire tree or that part of a tree will break and fall within a given period of time. So does every tree have a likelihood of failure? Yes. Every tree, if it's standing, is at some point going to die and fall over or break and fall over or be ripped out of the ground and thrown 100 yards. Every tree has that potential. What we're talking here is what's the likelihood that that's actually going to happen? What are the contributing factors that are going to make that worse? Trees or their parts will fail when the load they experience exceeds their structural capacity. You know, you cannot change the laws of physics. If a branch can only support, the branch has a load limit of 5,000 pounds and there's 6,000 pounds, it's experiencing 6,000 pounds of load, it will break. It has exceeded its load capacity. You know, this might happen in a really long branch. In a windstorm, the wind might add just enough load to it that it's going to break, or bifurcated trees, all that sort of stuff. Targets, these are people or property that could be damaged or injured if the tree failed. So a target, you know, whatever has the likelihood to fail, and it's going to experience a load that'll cause it to fail. And when it breaks or when it falls, it hits a bedroom. A bedroom is usually occupied 8 to 9 hours a day. So there's a good chance somebody's going to be in it. It is significant property because it's a house, right? So you paid a lot of money for your house. There might be a person in there, and what's the likelihood that they can be impacted? You know, so if you have a third of your day where someone's occupying a room, you've got a pretty high chance that somebody's going to be in there. So that makes the target very significant. However, without a target, there is no risk. You know, if Weyerhaeuser has, 50,000 acres of Southeast Texas here, and a pine tree falls over in the middle of that acreage, what's the target? Well, the target there, because it's Weyerhaeuser, they're raising commercial timber, is going to be the value of whatever is knocked over, but it's just going to be a tree. There's almost no likelihood a person is going to be there, and the property that would be damaged would just be the tree. So there's still some value to that target. If it were the middle of the woods and no one really owns it, maybe it's public land, the value of the target is going to be really low. Not going to be zero, but it's going to be really low enough to say that there is no risk associated with that falling tree or part of tree. So potential of the tree to fail can be based on the species, the condition of the root system, branch attachments, defects, and history of the tree. Another thing that is very difficult for arborists to detect might be soil problems. Not all trees that fall over fell because of a defect in the tree. It could have been a defect in the soil environment. So it could be a soil failure. So there's tree failures and soil failures. So this is particular to a tree fail. Structural defects can amplify that. So if you have decay or other faults in the trunk or the branches or the root collar of a tree, these might lead to failure. So these are examples of defects that could lead to a failure. Environmental conditions that could have a factor, obviously here where wind is going to be a big one. So storms, wind, lightning, construction damage. Construction, can change the environment that a tree sits in. Where it used to be in a woods, now it's exposed and it didn't prepare itself to be exposed. Grade changes where you cut the roots, or soil conditions, again, like the soil failures that we talked about. So risk management is evaluation of trees for their potential to fail and how you're going to manage that risk. Almost all trees pose a risk of failure. Like I said, if they're standing, at some point they're going to fall over, either after they're dead or while they're still alive. The more mature the tree is, the greater the risk. So the bigger the tree is, The heavier it is, the more mass it has, the further it has to fall, so it's going to accelerate more. And so again, we go back to that M times E to give you force, which can create a lot of damage. Also, mature trees, if you think about them over time, the longer a tree lives, the closer it gets to falling over, because we've already established that all trees at some point will fall over. So the longer in its life it goes, the closer it's going to get to that point. So there's sort of twofold there, both from a mass and a time standpoint. We classify risk assessments into three basic categories. Level 1 might be a visual only, and this doesn't mean getting out, walking around the tree, that sort of thing. Typically, this would mean a windshield investigation. This might be good if you have, if you're a city manager or something, and you're in charge of all the trees in the city. It's going to be more responsible of you to drive down and look for trees with potential failure. You're doing them a lot of the time. You're collecting a lot of information, and you're just trying to start your assessment. So you might see some that stand out to you as, well, these could be a problem. This one's leaning over the roadway. This one's next to the power lines. Doesn't look like they've come back and taken care of that in the last 10 years. They need to do that. And so you might escalate the standing of a particular tree to a level 2 risk assessment. Every time as a salesperson, and I write bids and estimates as part of what I do in my company. So when I go out there, I'm telling everybody in my contract, you are receiving a level 1 assessment unless you ask me to do otherwise. And I'm only looking at that portion of the property which you ask me to look at. And I'm not commenting or assessing any trees that have not been asked to look at. So I'm being very precise in my language as to what I'll look at, what I won't look at, and the level at which I'm giving them. So if I just step onto a site to look at pruning, they are getting a level 1 visual assessment of the tree that they're asking me to look at. However, if there's something about that tree that suggests maybe the whole tree could fail, or they're going to pay me to look at a tree and document that answer, that's immediately going to become a level 2. So level 2, I'm going to touch, measure, inventory. I might thump on it with a mallet. I'm going to document it. I'm going to document all these measurements and findings, but it's sort of non-invasive. So I'm not using an exceptional piece of equipment or doing an exceptional means. Like you saw, if you were around, saw some of the pictures of Jimmy climbing the tree, he was actually doing a climbing risk assessment for me. So I had done everything I could on the ground, but standing on the ground, you can only see so much, or you might hear only so much when you're getting feedback. But if you're looking up into the canopy and you see sort of the language of the tree telling you that there's a problem, but you can't quantify it, you're going to have to do something like climb the tree. And that would be a level 3. So level 3 is going to be a level 2. That's additional testing that could be invasive, like tomography or resistograph, or it could just be an extra expense such as climbing. So it's something extraordinary. What are we going to do? We're going to examine the overall health and structure of the tree. And we might even say condition, health, structure, and condition, depending on all the different facets there. Health and condition or structure can be totally independent issues. You can have a Bradford pear that's 11 and a half years old that is in perfect health. There is nothing wrong with it. It's growing like gangbusters, but we know structurally it's about to become a disaster. So always make sure that you're separating these two, that you comment on health and structure independent of each other. So you don't say that the tree's in bad health because it has poor structure. It can be in excellent health and poor structure. Look for things out of the ordinary. Look for things that's not part of the system. Every time I go out and do an assessment, I'm collecting visual data in my head about what normal looks like and what abnormal looks like. So if you have an assessor that's been doing assessments for most of their lives, they're going to be able to detect a lot of defects in trees that someone else might not see. But also we can associate over time those defects with actual failures. I've worked lots of hurricanes and tornadoes and floods and all types of natural disasters and accidents that have happened, vehicular accidents. I've seen a lot of trees fail, and I've been able to remember what those trees look like and what their defects were and how that defect impacted their failure. And so somebody who's never done these before is going to have a different viewpoint than someone that's been doing it for 33 years now. Not that I'm necessarily better at doing it, but the more information that you collect, the better you're going to be at these. So you'll get better and better over time. And when I say the language of the tree, what I'm really talking about is the response growth. If you look for that book I talked about earlier from Klaus Medic, The Body Language of Trees, we talk about response growth or reaction wood and how, like a leaning tree is going to be oval compared to an upright tree, that sort of thing. So it's going to have a different look to it. So if I have a leaning tree that looks round, I'm going to say, well, something looks a little sketchy there. Look for uplifted roots, look for broken roots. Up in the canopy, you might want to look for dead portions of the canopy, gaps or discoloration in the crown. An example here, I've had a lot of people say my tree's is chlorotic. I need you to come out and do an iron treatment, and I show up and it's really freeze damage. It has killed off a lot of the vascular tissue, and it just can't get enough elements out there to the canopy to get it fully green. But it did alert me that there was vascular damage. Whenever there's vascular damage, there's going to be decay. So at some point in the future, there's going to be an increasing risk of failure with those trees. Gaps in the canopy. If you have a branch that's here in a nice round canopy, if it falls, it's going to stick out further. And where it fell from is going to leave a gap. So you're going to see airspace where there shouldn't be airspace when you're looking up under the tree to the sky. And you might see a branch that sticks out a little further than it should. Look for trunk taper. Trunks should be wider at the bottom than they are at the top. We've got some visual examples of those coming up. Make sure that you're examining the trunk, the root collar, and the root zone, kind of like we did in the plant healthcare assessment where we spiraled around the tree, where we're looking at the ground, we're looking at the top of the tree, we're looking closer to the root system, we're looking at the branch structure, we're looking at the compression plate, we're looking at the main stem, and now we're looking at the whole basal area of the tree. And we're doing this spiraling in, so we get 365-degree eyes on the tree, top to bottom. Do the same thing with visual assessments. That's going to take some of the bias out. You might have things that trigger you to go look at the tree closer, but once you're looking at the tree closer, make sure that you're doing this 360 visual assessment all the way around. Look for codominant stems and the associated included bark with them. Other things to look for, up at the tree canopy, you're looking for asymmetry in the canopy, low hanging branches. So again, a low hanging branch might be covering up a stop sign. It might be down in the face of somebody on a tractor that's mowing the area. It could be down in an area that impacts a golf course. I mean, there could be a number of reasons why low hanging branches could still be an issue. Foliage condition, again, look for dieback, look for the size of the leaves, look for chlorosis for some of the reasons I mentioned just a minute ago. Look at the crown structure. What's the branch attachment? We talked about this tight branching habit, and that is typically genetically replicated throughout the canopy. So if you have a codominant stem that's very tight, so you've got these two big leaders that are tight, if you look up into the canopy, you'll see out on branches that might be doing the same thing. So that same habit can replicate. So as a big giant water oak, when it's a little tiny one and you've got two sort of stick-sized branches doing this, remember each one of those stick-sized branches at some point in the future might be 20 inches in diameter each themselves. So there's a lot of force in there. So just keep all of that in mind. Look for bark on the branches and the trunk. Is the bark coming off? Is there, like here with the vascular damage, now the reaction tissue behind at the margins of where the vascular system froze is growing, and as it grows, it pops off the bark that was there. So is the bark popping off? What does the decay look like? Do you hear cavities when you thump on it? Do you see the cavity? Cavities that you can see that are open make the trunk weaker than the ones that are just contained on the inside of the trunk itself. look for, look at the bole or the trunk, look for cracks, splits, or excessive leans that don't make, especially ones that don't make sense. Examine the roots and the root flare. Look for conchs, look for rot, look for heavy soil compaction, look for flooded conditions, look for, was it planted too deep, look for girdling roots and all that sort of stuff. Again, the visual tree assessment here, look for the rotted, dead, decayed limbs throughout the canopy, the bole, the branches, or the roots. A lot of, you can have some of this rot that happens if you prune on the top side of the branch time and time again. You can develop sort of this column of decay that you can't even see from the ground. So if you suspect something, make sure and put a climber up there. Look for cracks or splits on the trunk or major branches. Look for past lightning damage that can mimic a split. It might look like a split, but a closer examination, it might not be. Mistletoe and fungi are indicators of perhaps declining health. Again, the closer the tree gets to dying, once the tree is dead, it becomes a higher liability of failing. Lightning, wind, or storm damage, insect infestation, improper pruning, epicormic branch structure. Like this could be lines tailing, could lead to decline or the transfer of the weight out to the tip of the branch, so it's not distributed along the branch anymore. The response, the epicormic branching. Maybe the tree itself is too close to the roadway. It's just planted too close to the road. And so as it grows in diameter, it might actually grow over and incorporate the road. You might have a line of sight obstruction from the vegetation. We talked about the contributing factors that things like ivy can have. Kudzu, English ivy, all those sorts of things can have an impact on the load that the tree has to bear. So by this point in the presentations, you guys should all know by now that included bark is a sign of a defect. So you're going to examine the branch angles, look for these tight ones versus the open ones, especially on the major scaffold branches. Branches should be smaller in diameter than their parent stems. Check for proper branch bark ridge formation. Remember, if you don't see a ridge formation, it's probably some type of inclusion. And again, we can sort of jump over that. We've seen it a lot. Here's an example. I talked about construction if you're on a construction site. So here's the big thick woods, and notice that these trees are relatively tall. Their canopies are way up high. There's not a lot of diameter change here from top to bottom. So because of that, there's very little taper. If right now, when the wind blows, the canopies experience the load. One tree bends a little bit, dumps it into the canopy of this tree, which might dump it into the canopy of this tree and into the canopy of that one. So it's very little movement. Even though the wind's very forceful, it doesn't have to move very far to offload to the next tree. And so if I were to carve these out and put a house here, all of a sudden I'm going to have a bunch of trees that are now facing weather that had never had to experience it on their own. The key thing to remember about the growth of trees is it's always in response to the stresses that they're under. The most common stressor a tree experiences is going to be gravity. The next one's probably sunlight. And the next one's probably wind, predominant winds. So always take that sort of stuff into consideration. These trees didn't have to experience the same forces that an open grown tree did. So if you carve this out, you're going to instantaneously change how that tree has spent the previous 50 years of its life. And so you have a high degree of failure. So look for that on new construction sites. Make sure the trees have taper or they're far enough away from the houses that you've taken the tree line away from the targets. Yeah. So again, we'll talk a little about this response growth. Here we have a tree that's growing out over a lake. The trees in the lake are non-existent. So sun is always going to be over the lake. So if you're on the edge of a forest or the edge of a lake, if there's a forest behind the tree is going to grow out towards where the sun is, because that's what one of the major stimuli is, if you recall phototropism. So it's going to grow out in that direction, but it's going to do a little bit every year. So if we were to look at a cross section of this stem, it's going to be oval in shape. So the tension wood will have overdeveloped. And so that's what's holding the tree up. Compared to this one, we have a slight lean, but you see how all this grass is nice and green. It's nice and green because this tree is shifting. It's moving a little bit and it's picking up the soil on this side. We have a number of things going on here. Notice that there's a change in color of the sidewalk. And notice how clean this driveway is. It still has some cracks in it, but so this might be original, but this section looks like it is new out here compared to this section back here. And so remember, we talked about that compression plate. It goes several feet away from the tree in all directions. So, the compression plate of this tree would probably be out here somewhere. It's going to be deformed by that sidewalk and go around the back side of the tree and connect. So if the tree is falling in this direction, that compression plate's going to pick up in this direction. So hopefully you guys can see all that stuff on laser. Here's some examples of how reaction wood forms, the difference between conifers and hardwoods. So remember, conifers are going to have pitch tubes. So conifers do not have to be evergreen. They just have to make cones. That's where the name comes from, cone, conifer. So over here we have a hardwood. Hardwoods are said to develop tension wood in response to gravity. So if we look at a branch that's coming straight off of a tree, just like this, here we're going to have tension wood on the top. We're going to have compression wood below it. So on this tree, we have very tight tension wood that develops here, and pretty open. See how this ring, again, that ring sort of collapses on the tension side up here. So if we were to draw this one around and look at that, and then look at the neck. Sorry, got off track. So as we go around, as it comes, see how that line gets a lot closer right there. And then as it comes up to the top, you can barely even tell it's a separate growth ring. See that? So this wood's the tension side of this, the top side is very, very strong. Over here, you have sort of normal growth on the top side of a conifer, but you have this excessive compression wood on the bottom side of the branch that's developed. So you might say, well, it kind of looks the same, Rob, but when you study it, you'll find out that, this is really exaggerated here on the bottom side compared to the top side. So here, just the way that they study it. So if we were to look at an upright branch, the typical growth habit of the main trunk of the tree is going to look more like this. So this part really isn't overdeveloped. This is just normal size growth increment, and it's being compacted up here with an increase in tension wood. Does this have an impact on the vascular tissue? It does, doesn't it? So if you stop to think about it, the vascular vessels are going to be much bigger here than they are here. So again, this has an impact on how you prune. So just don't want to go down another rabbit hole, but it does have an impact. And again, we'll go back to compartmentalization of decay in trees and how that pertains to risk assessment. So, growth rate and good compartmentalization are important in the reduction of hazards. For a period of time, the reaction tissue on each side of this wound, if you remember, I said an open wound is less stable than a closed wound, where you have a column without any opening to the surface of decay. So in the initial stages, these columns can actually bear the compressive weight that was borne by an entire trunk. But as the tree grows, this reaction tissue can actually cause some problems on the inside of the decay columns, the sort of ram's horning that can lead to further trunk failure. So if you do see this is an issue. Watch for cracks or splits. Let me see, I might have had a note here. So, I talk about this compartmentalization. So trees that do not compartmentalize very well, these are going to be things like maple trees, both the red maple and the sugar maple, the ash trees, the magnolias, the apple trees, pine trees, especially the Virginia pine, poplars, anything in the prunus family, and a few of the quick growing oak trees are going to be not so hot at compartmentalization. So just keep in mind that when you're looking at the species over here. So again, we have these sort of faults and defects in the trees. Here's a tree that's splitting apart. Is this tree at high risk for failure? Yes. Is it a high risk? Well, remember, risk also incorporates the target. So make sure that you're considering the target. If this is out in the open and it's a cattle pasture, the risk is going to be fairly low. But you can see that this is obviously what we call a state of active failure. So if this did actually have a target, this would be very high risk. Here's a pine tree. There's you can sort of see this wound pops out a little bit. On this one, that's would be caused by bird damage or something like that. This wound is an inward wound. This one's more like someone left a clothesline on it for too long. This inward one is much more dramatic than this one when it comes to potential failure. Obviously some trees can have a tremendous amount of failure on the inside, but they are so historically significant that we don't remove them. So this is a giant redwood in the Redwood National Forest, and notice the trail over here. Studies have actually shown that the amount of time that any one particular person spends on this trail in the drop zone of this tree is so insignificant that this tree is really not considered hazardous. It might be approaching high risk, but at some point they might put a fence or something around to keep you outside of the drop zone. But for now, they still have trails that go against these trees. Here's another bifurcation that you can see that's beginning to split apart here. Let me put this picture over here in perspective for you. This is an old pruning wound. This is from a climber's perspective looking back down at the ground. So there were two stems that came off very close together, and someone said, hey, I want to prune this one off so that the other branch can grow. Well, this other branch is trying to absorb the branch pocket of the one under it, but as a result, you sort of have this water collection area. Is this a huge problem? Well, the water is not so much of a problem, but the fact that the majority of the holding wood comes from the tension or the tensile strength and not the compressive strength, and here, right where the branch attaches, there's not a whole lot there to bind that to the other trunk. So this is still an issue, but it might be only something you would see while climbing. So I encourage you to take a Coke can or a beverage can or a beer can, drink the contents, set it down without deforming the edges of the aluminum can, and stand on top of it with one foot. And what you'll find out is that can bear about 200 pounds without crushing. But as soon as you put a little nick in the side of the can, the whole thing falls apart. What that tells us is, as the engineers tell us, that means that the majority of the strength of any cylinder is on the surface. And so the tree can be missing an awful lot of heartwood and still be just as structurally sound as if it were solid all the way through. Now this one, you can see sort of the discoloration on this edge. You can see the white on this edge. So there wasn't a whole lot of holding wood here, just a couple of inches of thickness. You can see it, maybe 3 or 4 inches of shell wall thickness. So that's wasn't enough, obviously, to hold it up. But did this happen overnight? No, it held on for decades, probably, with enough decay to have failed. We'll talk about some potentials in a minute. So, but the things you want to look for again are cracks, seams that not something you would expect, abnormal butt swell, and again, compare that to the species like a scarlet oak. All scarlet oaks are going to have this butt swell. So if it's not a scarlet oak and you see this swollen area at the base, so you can see this sort of swollen look to this trunk. It's not right. So something there would have told a trained arborist to look a little deeper. Look for asymmetry. Is it ovate in shape or is it round? Look for dead branch stubs or old pruning wounds that might have hollowed out, things like that. Again, so codominant stems, these are going to be a higher potential for failure. Look for multiple branch attachments, like on this linden, you see a bunch of them. This would be sort of the same categories the Bradford pear might fall under. Look for cracks or separations in the soil. Remember that compression plate. Remember that failure that we talked about. And I said when the tree falls over, you see that disc of dirt that hangs out. That's that compression plate. So if you're going to see a failure, structural failure, you're likely it's going to show up in that compression plate. So any damage in that compression plate is a big deal. Examine it closely, consider it carefully for how that's going to contribute to the overall risk of the tree. You know, here we have, if you look closely at the road here, you can see that there is a brand new section here and a new section of curb. So that tells me that they probably did something. And over here on this one, you can see this section has been cut. So this could have been a sewer line replacement, something like that. And the sewer line might have come from this point, gone directly to the house back here, something like that, cutting all the roots on this side. And so the tree falls over. Here we had limited root space to begin with, and we take a big chunk of that out. And again, we have tree failure. So think about these things before they failed. You know, they would have looked like pretty normal trees. Take the time to do the investigation. Do that 360. Look for these things like the different color asphalt. Look for the new sidewalk or curbing. Look for where maybe they were doing risk mitigation on the sidewalk, where they might have shaved roots off that were growing over the sidewalk or shaved the sidewalk down. Things that have impact on the root system. Here are some examples of cankers and wounds and how they contribute. You've all seen these pine trees that have sort of the wound in them that looks like this. And along the edges, you might see this sort of orangey dust, like you can see all through here. Those are spores being produced from fusiform canker. So the pine trees will harbor this canker year after year after year and respond to it. And so eventually you get these sort of faces in there. In the early stages, it does not have any significant impact on structural integrity. It does impact efficiency of the vascular system, especially at this young stage, and it can kill them if it's a significant enough infection at this young stage. Now, if it impacts them once they get older, it's not quite so bad. This might have been caused, I call this roll-off damage. So when they roll off those big dumpsters and they want them to roll into something, so they stop rolling, that could have rolled into the base of this tree. Someone could have been backing out of a driveway and hit this tree with a bumper, a moving truck or something like that, or a bobcat. And this is the resulting damage over time. This is all wall 4 of the reaction. And notice it's square. Look over in the corner of the square, you'll see a crack because this reaction tissue ran into this reaction tissue, and it's actually 2 separate entities. It's not continuous like it would be on a proper pruning wound. Cankers can also have an impact. You know, this could have been a maple borer and things like that you know, creates this canker, or it could be fire blight and create a canker that looks something like this. All the cankers change the density of the wood. Same thing with galls. It changes the density of the wood in the location of the defect. And just like a guitar string, you want a guitar string to be the same material top to bottom, the same density of material, same manufacturing process. As soon as you put a defect on it, it changes how that string sounds, such as when you put your finger on it. When you put your finger on it, you stretch it a little bit and you push it against the fret a little bit. And so you change how that thing vibrates. That's sort of what these things do. It's kind of like putting your finger on it. We hit a little on this during the guying and cabling portion. So you're changing how the tree loads and unloads. So something like what trees with these types of cankers might be more prone to, or they are more prone to failure than trees without them if all other things remain the same. you might have mite damage that impacts the trees. Some mites lay eggs in the trunk. Some insects lay eggs that create galls into the future. Some of these can actually be cancerous in nature. You can have fungi, bacteria, or nematodes that cause knots in the woods or in the roots. So we have abiotic damage. We talked about the trucks backing into things, stuff like that. Here's this tree. It's totally surrounded by asphalt all the way around. Probably not the best growing environment for a tree. And here we have a tree that is in a construction site. Think about this tree a year from now when we have noticed that this is where the dirt's going to be up here. Let's see where the brick stops. So they're going to backfill all this and make a slope in the front yard. So if you made a slope in this front yard, the slope's going to go like this. Right? So as the slope goes like that, notice where that line crosses these trees. So the actual trunks, and then this one's burying most of the root system. So you've buried all of the critical root system of these two trees, plus you've buried the trunks 3, 4, 5 feet deep. But you come back in a couple of years and those trees are still going to look happy because they had lots of reserve stored up in them. But what you're going to look for is there's no flare on that new slope. It's just going to go straight down into the ground with no flare because the flare is way down here. This is where the trees flare out. You can see the flares on this one and coming out this way. So these, and same here, you see root going off. So all the flares are going to be buried here. You wouldn't see them. It's just going to be like a stovepipe into the ground. So look for that sort of weirdness. As fungi digest wood, they decrease its strength. So fungal decay is a pretty big deal. You can identify fungi usually from their fruiting structures, like what the mushroom looks like, what the conch looks like. But keep in mind, they don't always make fruiting bodies. Everything has to line up for them to reproduce. So they might not be reproducing. They might not be reproducing at the time of the year that you look at it. So when you are doing annual inspections on trees, you don't have to do them at the same time of year. You might want to rotate seasons so that you're looking at it in the summer one year, the fall the next year, maybe the winter the following year, and then the spring the following year after that. So you're rotating around. You're looking for things like fruiting structures that might not show up but for a couple of months out of the year, or might not show up at all. Why are these things so important? Well, remember we talked about lignin in cells, and we talked about cellulose in cells. Some rots enjoy eating lignin. Some rots enjoy eating cellulose, and some rots eat both. So we have, white rots in general are going to be lignin digesters. Brown rots are going to be cellulose digesters. Soft rots are similar to a brown rot in that it degrades the cellulose and has some characteristics, however, of both the white and brown rots. So anytime you're munching away at the bricks on a house, eventually the house or the wall is going to fall down, right? Well, the lignin and the cellulose is what makes the bricks. So if you erode away either one or both, you're going to lose structural integrity over time. So decay happens at some rate. So just because it has these decay structures in it does not mean that it's going to fail today. It does not mean that it has eroded away enough of it for the whole tree to fail, but it will at some point. These types of rots, you really can't stop them. There's nothing that you can do to slow them down other than making the tree a little healthier. If it's a young tree, you might be able to accelerate the growth or the amount of good wood to dead wood, but once the pathogen is there, it's going to just keep doing its deal. At some point in the future, it will have eroded enough lignin or cellulose to cause decay or tree failure. So you have an increasing risk. So during your risk assessment, you might note, this is the fruiting structure we found. This is the related fungi to it. You might recommend additional testing, such as resistograph testing or tomography or something like that. That's going to give you more answers about how much is actually damaged. Some examples of lignin digesters are going to be armillaria and Ganoderma. These are both fairly common, especially in metro Atlanta area. So basal rot, this is going to happen down at the base of the tree. Heartwood rot, just like it sounds, it's decay that starts in the heartwood of the tree. Rarely does heartwood rot extend or make its way into sapwood, but remember, every year the tree's contributing an older xylem ring to the heartwood. So the heartwood's just going to keep pace. So as the amount of sapwood slows down or lessens in thickness, at some point the heartwood rot could catch up to the point where it might look something like that. Decay located in the sapwood is called sapwood rot. You might see sapwood rot show up in cherries are a pretty good example. So you see those little ear mushrooms that go up the side, that would be a sapwood rot. Decay can cause significant loss in strength. If the tree has 30 to 35% loss of sound wood to decay wood, action should be taken to remove the branch or tree. So what that's saying is if the decay area represents more than 33% of the total volume of the tree, then you're going to have an issue. There are calculations and stuff that you can run to drill this down a little closer, but really this ratio is what it's all about, this 30 to 35%. You might say, well, where do these things come from? Well, Clark and Matheny started this thing called the Tree Failure Database, and everyone contributes to this database on trees that have fallen apart. And what they have discovered is that there's kind of this bell curve to failures as it relates to structural strength loss. So as you're approaching this 30 to 35% strength loss, this is where the majority of failures happen in the bell curve. But as you know, there's what's called outliers on both ends of the bell curve. So trees can fail with hardly any decay, and trees might make it all the way to this. This is like 90-something% structural strength loss, and it didn't get there overnight. This tree has stood here for decades decaying until one day it finally got the right set of storm circumstances to knock it down. This tree was just over here, just out of sight, is a playground. Here's a parking area. This is a city park. Notice there's a little bench over here, and it destroyed that bench. So this should have been something that was mitigated a long time ago, but it wasn't. It was overlooked. Some other signs of internal decay, you might be able to literally see it like this. You might see a split or a bifurcation. In this case, this tree is a trifurcated tree. There's 3 trunks growing together. These 3 trunks are moving a little bit separately in the wind. And so you get some tears in the vascular system. Then it gets a yeast infection, and you get this ooze, this sort of bacterial wetwood or bacterial ooze resulting from it. So that can tell you that there's internal decay as well. You can also see the actual fruiting structure. Remember, this is not the fungi doing the work. This is the fruiting structure. So it's like saying an apple on an apple tree. So the apple is insignificant really to the overall tree. But a huge apple tree can make 1 apple, or it can make bushels of apples. Same sort of thing with the fungi. You can have a little bit of decay and a lot of fruiting structures, and you can also have an enormous amount of decay in just a few fruiting structures. So there's no direct correlation between the size or number to the extent of the decay on the inside. You have to do additional testing to find that out, to see what else to look for. Like I said, in additional investigation may be needed. You might use things like a resistograph or just a long drill bit where you're drilling into the tree and you're trying to feel your way through to feel decay. You might have to do a climbing inspection. Remember that filling a cavity does more harm than good, and because trees live for hundreds of years, you might still be running into trees that have cavities filled with concrete. It might even be very artfully done, but it's still very bad for the tree, and it accelerates the decay behind that. And as you have a rigid body, the filling, versus an organic, moving, dynamic structure over a rigid structure, when it moves, it's injuring itself on that rigid structure on the inside. So they can definitely do more harm than good. And things can happen under the root system, like we talked about, the root nematodes that cause these sort of knots on the root system. you wouldn't be able to see those unless you did a little more investigative work. Or if you have those conchs growing on the side of the tree, well, maybe you want to look for visual signs of decay. So, you might do a root collar investigation and find out this decay goes all the way around the tree, which you wouldn't have known if it was still covered in grass. You would never have discovered that. This device this looks like the air spade. So there's air spade. This is an air excavation device. And what they're performing is a root collar excavation. So you're moving the dirt away from the collar, exposing it so that you can see some of these roots. The air tool here, the pneumatic device, does very, very little damage biologically. So you're not tearing up the roots like you would be if you were using water or some other type of device, or a trowel or digging tool, physical digging tool, where you could injure the roots or the covering on the roots. This thing is very sympathetic to the root system. Some other tools out there, you have resonance testing. Is you've got something like a mallet and you're thumping the side of the tree and you're listening for hollow. A friend of mine, Jesse Milton, the consulting arborist who has a background and degree in music, is very attuned to this. He can thump on the sides of the tree, and often he can even tell you what species it is with a blindfold on just by listening. So this, if you were practiced, resonance testing can be an excellent tool. If you have an open cavity, it can be as simple as just measuring it with a stick. You're putting a yardstick inside, you're putting a metal probe inside, and then measuring how far the probe went in, things like that. So you can get easy measurements that way. Increment borers, this is sort of a hollow drill bit. So as you're screwing it into the tree, it's cutting out this sort of hollow section that fills the drill bit as it goes in. And then you can pull that out, and that's called an increment borer, because you can look at the growth increments. And you can also look to see, if you've got a 5-inch increment borer and you go in all 5 inches and you pull it out and you only have 2 inches of wood there, you know that there's 3 inches of hollow behind it, stuff like that. Other, detection devices, you have a resistance recording drill. A resistograph is an example of that. So as you're drilling into the tree, it's producing, or it's reading the torque on the bit and translating that torque one-to-one on a piece of paper or on a screen. So it's showing you how much resistance the bit's experiencing. So if you were looking at a solid tree, the bit would experience more and more and more and more resistance, or more torques required to drive it at the same speed into the tree. So that's a nice healthy tree, because you've got a longer bit, it's going to go up. If it goes up, 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 and then drops down, it goes up, 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 and drops down, and goes up, 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 and then drops down to nothing, you know that there's some lines of incipient decay in there where the decay is just beginning, some pockets, and then you run into a full-blown hollow area on the inside. So that can be a good tool. However, it only measures at the place where you actually measure. So it's up to the arborist still, because you're not doing this thing all over the tree. You turn it into a pincushion. So you have to make some determination. What is the worst area? If I'm thumping with it on a hammer, it's like, okay, it's more and more hollow the higher I get. Well, this is as high as I can reach and use a resistograph. So I'm going to make my measurement here because it sounds the worst here as I go up the tree. So I make them there. And if it's already 33% strength loss, you don't need to go higher in the canopy. However, if you're at like 20% strength loss, but it sounds like it's going to get more and more hollow, you might want to do a climbing investigation and do another one higher up the stem and see if at some point you do reach that ratio greater than 33% structural strength loss. There is another one, though, called an acoustic measurement device that produces, or called a tomograph, that produces a picture of the inside of the tree. So this one, you have a bunch of receivers that use these sort of nails with the transducers on them, and they go up the side and around the tree. And then you have a place where you're emitting a ping, sort of like sonar or something. So you've got this on the side of the tree, you're smacking it, and the sound wave travels through the tree, and it's picked up by all these other receivers going up the tree. As it's doing that, it's reading out onto a laptop or something like that, and it gives you a 3-dimensional picture of what you're looking at. So it's not, with the resistograph, it was worst case scenario. With the tomograph, you might discover where the worst case scenario is because you're getting a three-dimensional image, especially if you're starting down in the root system. You can detect the decay in the roots much more easily than you can any other way. But this, tomography can be very cost prohibitive. We're talking approaching big dollars. And resistograph tools can also be big dollars. These things are now in the $4,000, $5,000, $6,000 range and higher, depending on what you want it to do. Tomographs can start at 10,000 and go up. So they can be very expensive. So if you're not doing decay detection as a living, you might not run into these devices often. So, but they are out there. Documentation. I can't stress enough the need for documentation when it comes to risk assessments. Use hazard assessment forms to ensure that you're doing it consistently. These forms are going to remind you of things that you might have overlooked, or it helps to take out the bias of the assessment. Record all your observations, your measurements, and recommendations. This includes who the client is, who you talked to, who showed up on site. Did the next door neighbor come over and talk to you? What's their name? What's their address? If the failure site, if the tree were to fall onto a neighbor's property, make sure you're recording all the neighbor information. Record as much as you can. Record what the hazard potentials are and what the targets are. And there could be more than one target. What's the maintenance history of the site? And another thing to record is what's the failure history. Remember, when you're called out there, you get a static looking time, and you need a longitudinal looking time. One over is a significant amount of time. Like water oaks they can establish a history of failure. So they can pop a branch off for no apparent reason, probably associated with drought or something like that. But they pop off for no apparent reason without any wind. 2 years later, another big branch does it. 2 years later, another big branch does it. So after 3 times, you've established a history of failure and an increased risk associated with that tree, and you have an obligation to do something about it if there's a significant target. Now, I've worked with Dr. Clark and Nelda Matheny in limited capacities. They're both super intelligent. They do this sort of thing for a living. They're out in California, but they develop the photographic guide to the evaluation of hazard trees in urban areas. Until you take the track course, I highly recommend that you add this book to your library and read through it, because these are the people that really started it all. We need to talk about what some of the mitigation options are. Before the tree fails. Is removal necessary? That's not always what it takes. So the mitigation is the process of reducing the damage or the risk. Dead or broken branches can be removed. You can prune to reduce the weight of the limbs. You can subordinate prune so that in the case of codominance, you are creating one stem more dominant than the other over time, working out this codominance. You can move the target. If you park in the same place every day, well, maybe if you just stop parking there, you've changed the target, and so you've changed the risk level. You can install cables, embracing, and lightning protection. These things can reduce the risk before the tree becomes a hazard, but they cannot change a tree from a hazard to high risk. So just keep that in mind. So don't think, if you have a branch out there that's covering up a stop sign and you prune that branch off, you've instantaneously changed that from a hazard tree to a tree of very low risk with a minimal amount of effort. You cannot do that by installing lightning protection cables or braces. You can just reduce the level if you're doing it before the tree becomes that hazard level. But the whole thing still needs to be continually monitored. If not, then you have to have some way of assessing liability and ownership. So again, kind of like when we installed cables, bracing, and lightning protection, we talked about the liability associated with those. Same thing goes here. I'm very clear in my reports that my assessment is good for the day that I was there, for the things that I've seen, and I list out how I did it, what my level of assessment was, all that sort of stuff, and it's not good beyond that. because the likelihood someone's going to keep calling you back is fairly low. So you need to make sure and transfer the liability away from you and back onto the owner of the home, or get them to guarantee that they're going to allow you back for continued monitoring. Liability. When a person has suffered injury or damages, liability must be identified. Liability is based on cause. Causation means that the injury can be traced back to a defendant's action or lack of action. This, of course, does not account for unforeseen circumstances such as acts of God. That's a term. So arborists must understand their responsibility and liability that accompany tree risk assessments, because you now have a duty of care. Remember, you are the expert. Because you are the expert in tree care, you can be held to a much higher standard for inspecting and recognizing hazards, even if they were hired for purposes other than a tree risk assessment. Remember, I said that when I go out to place a bid on a property, I am telling them I'm giving them a level 1 risk assessment on the tree that they asked me to look at for whatever reason, whether it's fertilization or pruning or whatever. I'm telling them I gave them a level 1. This is the time period that it's good for. I'm very precise about that I'm not going to be held liable for something in their backyard that I was never asked to see. Document all the potential hazards. If you can see the hazard, you still have to document it. So even if, like I was hired to look at one tree and there's another one right next to it that is a disaster tree, I'm still obliged to tell them that this tree is a disaster, and then I document that that tree is super high risk for failure, even if I wasn't asked to. You have some duty of care there, even if you're not paid to render that opinion. Negligence is the failure to exercise due care. That means you were told the tree is going to fall and you did nothing about it. You are negligent. This occurs when someone fails to perform a duty or obligation recognized by law for the protection of others against unreasonable risk. Causation, in fact, means that the damage, injury, or death can be traced back to the defendant's action or lack of action. For proximate cause, the injury has to be reasonably foreseeable. So there in Atlanta, they had this case. It was a tree that was inside of a daycare, and a branch broke off and hit a young boy in the head. And I think he eventually died. I think his name was Tripp or something like that. But, here it was, the tree was in a play area. The branch was obviously dead. I saw the tree on the news, and they showed the tree, they showed the branch on the ground, and you could see hypoxylin canker all over the branch, like significantly on the branch, which means I knew the branch itself was probably dead or just about dead. It was certainly dying, was certainly recognizable that it should have been removed. However, they cleaned the site up rapidly, and so when they came back to start to figure out who to assess blame on, there wasn't anything to look at. A friend of mine got the case, and he's looking at it, and he's like, "Rob, I just don't know what to do here. It looks like the tree was in pretty good shape, because the rest of the tree sort of looked okay, but it hadn't been pruned in a long time." But they had not hired an arborist to come out and look at it, but they're asking an arborist to assess it after the fact. So they were looking for this causation, in fact, that someone not react. If something is dead, that means it's casually obvious. That means it's obvious to an untrained observer. Someone just walking down the street can say, "Hey, there's a big 10-inch dead branch there right over the play area inside of a daycare. Maybe somebody should do something about that." So he didn't know what to do. And I said, "Jesse, I saw that branch in the news report from the day that it happened, and it had hypoxylin. Maybe you want to, find out if you can get that piece of film from the news agency." And they did, and they were able to prove that the branch had that, and they should have known.
Rob,
Yes.
Rick wants to know, is it a good idea for arborists to carry a liability insurance policy?
And so the short answer is that you should always have a GL policy. at the very minimum, even if you don't carry workers' comp, you should certainly have a general liability policy to help you on these things. And since I do these things on occasions, I carry an umbrella policy on me personally. So if whatever my GL policy doesn't cover and they come after me, I still have plenty of money to cover it with my umbrella policy. If I did these on a regular basis, I would even get errors and omissions insurance. Errors and omissions insurance is quite costly though. So you have to be doing enough of these things to pay for it. Like I talk about my friend Jesse a lot. He's a board certified master arborist, carries all these sorts of things. So when I would get these cases related to injury and death, I would immediately just give them to him since he does more of those sorts of things. So there are different levels of insurance and different levels of responsibility. And obviously anything could happen to any of us on any site. So it just depends on what your personal level of risk is as to how far you want to take that insurance. Hopefully that sort of answers your policy before you get into trees and law, which is a big deal. So it's good to listen to the professionals talk about it. Any tree inspection performed, so this is sort of a municipal policy that is instituted in different areas around the country. Any tree inspections performed while our arborists are on site for any purpose will be considered a level 1 assessment per ANSI A300 Part 9 standard and will only identify the most obvious defects or needs associated with the tree defects. More thorough and documented assessments, level 2, can be performed for a fee upon request. You know how tree care guys always have these whole back page of all their disclaimers, and those disclaimers, are usually things about broken sidewalks and this, that, and other cranes. But one like this can also help protect you and the guys just out there doing your estimates for you. Since they are arborists, especially if they're certified arborists, they're going to be held to this higher standard. So good idea to have some type of policy like this in place. Now, here's some of the new vocabulary that you would see in the track. Assessment levels 1, 2, and 3. So we have the likelihood of failure, and these are the sort of rankings here going from its imminent likelihood of failure down to improbable. Your impact is going to be high to very low. Your consequences could be severe down to negligible. Some other terms that you should look at closely are going to be the defect, the load, response growth, risk rating, residual risk. Like if I prune that branch back from the stop sign, I've eliminated that risk, but 5 or 10 years later, it could grow back towards the stop sign. So there is going to be some residual risk after I prune it, and some sort of re-inspection frequency on the tree needs to be established. So this is just some of the vocabulary. They've it's made much more vague, and it's sort of more vague for a reason, because you're trying to get the point across of, in general, if something should fail or not fail and what the liabilities involved there are. And then lastly, we talk about the act of God. This is an occurrence due to natural causes that could not have been prevented by ordinary skill and foresight. So again, questions, be sure to shoot me emails or anything like that if you have additional questions. Let me see, I'm going to stop my share so that we bring everybody back up.
And I am here. It looks like I got stood up for my meeting. So
Uh-oh. All
and
right,
y'all, yeah, I mentioned the trees and law, and I got excited about that one, but we also have the insurance as well. So both of them kind of support each other. So in September, we'll be having one specifically on insurance for the arborist.
So I don't see any questions popping up there. So
No, none yet.
Again, I'm sorry, go ahead.
I was saying while we're waiting, I'll go ahead and steal back just so I can get my stuff set up here. There we go. All right, what you got to tell us, Rob?
I was just going to say, I can't stress enough how important it is, especially the topics that we covered today, to get out and see it in person, put your hands on it, watch people perform these actions, watch them perform, how they tie knots, how rigging works. It's very difficult to convey how all these things, what they look like and the amount of time that we have. And when these exams were originally produced, they strongly wanted you to have been out in the field for several years being exposed to all this stuff. And now we have a much wider variety of practicing arborists that are not exposed to these things. So if you've never been exposed to climbing aspects of it and to the safety end of it, delve into it. So from the safety perspective, get those ANSI standards and read through them before the exam. When it comes to rope and worksite safety, go look up a TCIA accredited company, Tree Care Industry Association accreditation, which is a very, very high level that they had to prove that they had safety programs. They have to prove their climbers are doing the right thing and highly trained on a weekly basis, that sort of thing. So, and there's tons of them in Atlanta. So find yourself a TCIA accredited company and ask if you can go out and watch. And there's some guys in this who are watching this who are also very well qualified.